Okay, so I'm going to start off with the first question here, and it's on DRAM refresh utilization. And so we start off with this large paragraph here that describes the system that we're going to deal with. So let's go through that. So here we see that the system has 4 channels, and so I'm just going to write this configuration up here so that we have that a little bit summarized. So we have 4 channels, and each channel has 2 ranks, right? So that's 2 ranks of DRAM chips, right? And so each memory channel is controlled by a separate memory controller, okay? So that means we have 4 memory controllers, right? And so each rank contains 8 banks. So we have 8 banks, and then a bank contains 32K rows. So we have 32K rows, and each row in one bank is 8 kilobytes, right? So we have 8 kilobytes, okay? And so then we start talking about, retention time and stuff, but this is our configuration. And so I'm just going to here quickly enumerate the values here of how many of each of these we have in the system, right? Because we're going to use that throughout the rest of the question. And so if I quickly make a table of these, right? So let's say the number of these that we have total, not total actually, let's just convert these to powers of 2 first, because we're going to have to do a bunch of calculations with these. So this means we have 2 to the 2 channels, we have 2 to the 1 ranks, we have 2 to the 3 banks. 32K here would be 2 to the 15. 2 to the 15 rows, and then we have 8 kilobytes of data per row, which then is 2 to the 13 bytes, basically, per each of these, right? And so if we now try to ask how many of these total we have in the system, that's basically just, evaluating these multiplied down. So we have 2 to the 2 channels total in the system, and then that means we have 2 to the 1 plus 2, so 2 to the 3 ranks in the system. And then 3 plus 3, right? 2 to the 6 banks, and then 6 plus 15, so 2 to the 21 rows, and then 13 plus 21, so that's 2 to the 34 bytes in the entire device, right? And so in the entire system, rather. And so, 2 to the 34, I guess here is, like 16 gigabytes, right? So that's how large our system is. And so this is a system we're dealing with. Right, so now the question tells us that the minimum retention time among all the rows is 64 milliseconds. And so to ensure that no data is lost, every row is refreshed. So every row is refreshed once per 64 milliseconds, right? And this is done by initiating a command from the memory controller, which occupies the command bus for 5 nanoseconds, and an associated bank for 40 nanoseconds, right? So for each refresh operation. And so we're going to consider a 1.024 second span of time. Okay. And so here there's a definition. So we define utilization of a resource such as a bus or a bank as the fraction of total time for which the resource is occupied by a refresh command, right? Which is sort of the natural definition of utilization, right? Like how much, what proportion of time it's used. And so for all of these calculations, we can leave our answer in simplified form in terms of powers of 2 and powers of 10 and so forth. So we don't have to go do unnecessary math and waste time with that. So let's get to the first part of the question. So it asks us how many refresh commands are performed by the memory controllers during the 1.024 second period across all 4 memory channels, right? And so we know here that every DRAM row is refreshed every 64 milliseconds, right? So now if we're considering a 1.024 second period, then how many of these 64 millisecond refreshes, 64 millisecond periods are in this 1.024, right? So that's the first part. And so we have 1.024 seconds is, 1024 milliseconds. So we have 2 to the 10 milliseconds, and we're going to divide by 64 milliseconds, which is 2 to the 6, right? And so we have, this is a 2 to the 6 milliseconds as well. And so we end up with 2 to the 4 of these periods, right? So there's 16 refresh periods throughout this interval. And for each period, we refresh all of the DRAM rows, right? And so up here, we computed how many rows there are in the system because we're considering across all 4 channels. That's this value here, right? So our answer here is 2 to the 21 times 2 to the 4, right? Because every period, we're refreshing all 2 to the 21 rows, and we have 2 to the 4 refresh periods. And so it's actually fine to just leave our answer like that. Or, if we want, we can simplify it to the 2 to the 25 and leave it like this. But the answer is correct in either form, right? So the second part asks, what command bus utilization across all the memory channels is directly caused by DRAM refreshes, right? So here, what we know from the first part is that we have 2 to the 25 refreshes in the entire system per 1024 milliseconds, right? Yeah, okay, that's clear. Yeah, so this is what we've sort of computed for the first part. And so now we're asking about the command bus utilization, right? So remember from before that we have 4 different memory controllers, right? Because each memory channel is controlled by a separate memory controller. And so 2 to the 2 channels means also 2 to the 2 controllers, right? And so if this is 2 to the 25 refreshes for the whole system, there's 1 channel per memory controller. And so the total number of refreshes there, we actually have to divide by the total number of controllers. So we're going to multiply by 1 over 2 to the 2. And so 2 to the 25 over 2 to the 2 represents how many refreshes happen per channel, right? And so this is essentially the number of refreshes per channel over the 1024 millisecond period. And we want to know the utilization across that period, right? And so this information over here told us that every time a refresh operation happens, the command bus is occupied for 5 nanoseconds, right? So we have, so if the time units are down here, we have 5 nanoseconds for every single refresh command, right? And so the time units here cancel each other, right? So we have time and time, and this is number of refreshes. And so this is a unitless quantity, which is what we're expecting. And so then we can just leave our answer like this. We can leave it as 2 to the 25 times 5 nanoseconds over 1024 milliseconds times 2 to the 2, right? And so that's the answer to that part. And like you could go ahead and simplify if you wanted to. You could divide these powers of 2 and convert the time units to the same quantity, but it's correct as is. So the next part of the question asks what data bus utilization across all of these memory controllers, memory channels. It's directly caused by the DRAM refreshes, right? And so if we're asking about data bus utilization, then over here, every time we do a refresh operation, we're not exchanging any data, right? So trivially there, the answer is just 0, right? Because there's nothing happening on the data bus whatsoever. And the last part asks for what bank utilization on average across all banks is directly caused by DRAM refreshes. So how we approach this part of the question is very similar to the part B, right, where we asked about the command bus utilization. Except here we have, so here we had 4 different memory channels, and so we were trying to figure out the number of refreshes per channel, right? And here, if we're asking about banks, we want to figure out the number of refreshes per bank, right? And so we can start off with our same ratio because this is what's happening in the system. So we have 2 to the 25 refreshes per 1024 milliseconds. And so if we're asking about per bank, here we figured out that there are 2 to the 6 banks in the entire system, right? So we want to divide this number by 2 to the 6. And so this is the number of refreshes that go to a particular bank in this time period. And so in terms of the utilization, over here, the information told us that a bank is busy for 40 nanoseconds per refresh command. So here the scale factor was 5 nanoseconds. Over here, the scale factor will be 40 nanoseconds, right? So 40 nanoseconds per refresh. And so the computation is like exactly analogous to that, just with different values, right? So here we have 2 to the 25 times 40 nanoseconds over 1024 milliseconds times 2 to the 6. Right, and so this is the utilization. If you go ahead and evaluate these, I think the values are in the solutions we have online. Right, this is about 4%, and this is about 2%, right? And so if you did go ahead and compute that, that's what you would end up with. Okay, so are there any questions about that part so far? I'll move on to the next thing. Yeah, okay. So the next part of the question asks us to optimize this a little bit, right? So there's more text here. And so the system designer wants to reduce the overhead in order to improve system performance and reduce energy. Okay. So what we observe is that not all rows in the DRAM chip need to be refreshed every 64 milliseconds. And in fact, we only need to refresh some rows at lower values, which are indicated in this table, right? And so this table provides us with what we need. So there's 3 different refresh rates here, 64 milliseconds, 128, 256. And we have a different number of rows that fall into each of these buckets, right? 2 to the 5, 2 to the 9, and all other rows. And the question then asks us that given this distribution, if we only refresh all rows as necessary, how many refreshes are performed by all the memory controllers during the same time period across all 4 channels, right? So it's basically the same thing this guy asked for, except now we have different refresh rates. And then after that, we're asked about the command bus utilization, and then here, data bus utilization, bank utilization. So it's the same sort of computations we're going to do, right? Except here we have a different number of rows. So we started off here by defining how many of these 64 millisecond refresh periods were in the interval we're considering, right? And so it ended up being 2 to the 4. So we can do the same thing here and sort of, for each of these different refresh rates, compute the number of refresh intervals in a 1024 millisecond period. And so for 64 milliseconds, it's the same, right? There's 2 to the 4 of them. For 128, it's 2 to the 3, and for 256, it's 2 to the 2. And then the number of rows that are refreshed in each period, so we have 2 to the 5, 2 to the 9, and then all other rows. And so to figure out what that value is, we know the total number of rows in the system, which was 2 to the 21. And so we can simply write this as 2 to the 21 minus the rows that are specified, right? So minus 2 to the 9, minus 2 to the 5. And so now we have all these quantities. And so figuring out how many refreshes are necessary during this period is just multiplying those values through, right? It's nothing too complicated. So we have 2 to the 4 rows that we have 2 to the 5 rows that need to be refreshed 2 to the 4 times. So over there. And then we have 2 to the 9 rows that need to be refreshed 2 to the 3 times. And then we have this quantity of rows here, 2 to the 21 minus 2 to the 9 minus 2 to the 5. That needs to be refreshed 2 to the 2 times, right? And so that's the answer. And so again, we can leave it like this or simplify if we want to, right? Okay. So the next part is the command bus utilization. And so this computation is basically exactly the same as we do up here, right? Except instead of 2 to the 25 refreshes per channel, we essentially have a different value. And so instead of writing this repeatedly, I'm just going to define this as a variable n, right? So it just makes this a little bit easier. And so what we have here is that we have n refresh operations happening per 1024 milliseconds, right? Where we computed n in this part. And so we basically do the exact same thing as up here, right? So we have n refreshes total in the system, but we know that we have 4 different memory controllers and therefore 4 different channels. So we have to scale this by 4. So we essentially divide n by 2 to the 2, right? And so that's the number of refreshes per channel. And it's happening over this time period. And we know that each single refresh operation keeps the command bus busy for 5 nanoseconds, right? So 5 nanoseconds per one refresh. And so the answer then is just n times 5 nanoseconds over 1024 milliseconds times 2 to the 2, right? And once again, you could go ahead and simplify it. Based on the solutions, this ends up being like about 1%. So something like that. Yes?
So you consider that this command bus utilization is for
yeah. Right, so each channel experiences the exact same number of refreshes, right? Because there's the same number of rows. So, okay.
So you said up there that those are different intervals for different numbers of rows?
Yes.
But in the whole system?
Yeah. Okay. Yes. Absolutely. That's a very good point. And so here what I computed was assuming that these are uniformly distributed across the 4 channels, right? I guess I made that assumption without it being stated. Yeah, I think you need to make that assumption. And so if in a, say, an exam situation you thought about that, you could just write it here, like I'm assuming that whatever. And if you write that as we're grading, like as long as that assumption is reasonable and your answer makes sense based on the assumptions you made, that should be fine, right? Yeah. Okay. Is that fair? Yeah. Okay. Go ahead.
Can you, in an exam situation, leave your answers in terms of n or like an expression, or do you need to calculate it like you did as 1%?
No, that's right. So you don't have to do this 1% part. This was fine for homework because you could just plug this into like, calculator or whatever. In your exam, it's okay to leave it like this as long as it's clearly defined what you're doing. So here n, I very explicitly defined here. This is what I'm referring to, right? And so I think it's very clear when we're grading your exam that that's what you meant. If you do something strange or it's really hard to read, then it might get confusing for us to grade, and then you might lose points, and then it'll be a mess. But yeah, just be clear about it, and your expression should make sense, right? So I think here, writing it out like this, while it's not in the most simplified form, it's clear what you were computing. And so even if one of these values was wrong, right? Let's say you accidentally wrote 2 to the 6 here. Fine. It's still like your methodology is correct, and you'll get the partial credit that you deserve because you did the right thing. You just screwed up one value or something. Yeah. Okay. But, yeah, you had a question? I see. Are you saying that it was specified as bank here, or that it's ambiguous? Yes. Oh, I see. And so you're saying you can interpret this table either way based on that information? Yeah, sure. I think that's fine. And then just write it as your assumption. Does it? I mean, you just recompute your number of rows based on that information, right? Because if you assume each bank has this exact same ratio, then each channel will have the same number of refresh commands happening. So it wouldn't be ambiguous in this case. You just end up with a different value based on the number of rows. Yeah, it would just essentially balance the ratio towards these guys, right? So instead of this being, 2 to the 4 times 2 to the 6, it would be, all this done at a bank scale. And so you'd have a different ratio of each. I think that's fine. If the question allows you to interpret that way, then yeah, just state what you did. Yeah. Right. Is that fair? Okay. Yeah, are there any other questions? Okay, then I'll move on to the next part. Oh yeah, so we're still continuing this part, sorry. So here, can you see everything? Okay, yeah, sorry, I guess I'm sort of blocking that for some of you. I'll put it up here for now. So it's asking us the DRAM data bus utilization. And same as the first part, right? We're not utilizing the data bus, so this is easily just 0. And so then this asks us what the bank utilization is on average. And so again, here we can treat it kind of the same way we treated it for this part, right? And basically the same we're doing here, except it's just a different factor. And if you're making a different set of assumptions, then I guess you might do this a little bit differently. But the process should be the same, right? So here we had n refresh operations for the entire system per 1024 milliseconds, right? And so here we want to divide n by the number of banks in the system because we're assuming that it's equally divided among banks now, which is, I guess, the assumption that you stated, right? So, so here we have 2 to the 6 banks in the system. And so we're going to say that these refresh operations are equally distributed amongst banks, right? And so that's how we would arrive at this answer. And yeah, it's 40 nanoseconds per refresh operation. And so when we compute that, it's n times 40 nanoseconds over 1024 milliseconds times 2 to the 6, right? And yeah, I think, in the solutions, that's like about 0.5%. But yeah, so does that make sense? I think it's basically the same computation you did before. So now part H is asking that now we want to achieve this reduction refresh by refreshing rows less frequently. So in order to implement this improvement, the system needs to track every row's required refresh rate, right? And so what's the minimum number of bits required to track this information? So we need to track every row's required refresh rate, right? And so here are the refresh rates we're dealing with. And so there's exactly 3 refresh rates, which means there's 3 different states that we need to be able to identify for each row, right? And we know that there's 2 to the 21 rows, right? So we have 2 to the 21 rows times the number of bits to encode three states, right? And so that would be, sorry, yes?
I actually wrote an email about this.
Okay.
Because, you can use 2 bits to encode 3 states, but if you consider more rows, you can, for instance, use 5 bits to encode all the combinations of 3 rows. So,
right.
Really, you would have to multiply by log of base 2 of 3.
Yeah, I was actually about to write that exactly. Yeah. No, I mean, you're right. So there are different ways to do this, right?
It's just that it explicitly says minimum number of bits. So
yeah. So you went ahead and found a more optimal scheme.
Well, it's actually then optimal. You could not encode the information in fewer bits than that. I mean, no matter how you implement the algorithm for it,
right?
It's like
okay.
And question about information, you can
Yeah. So you found basically the information theoretic bound for encoding all the information that you need to encode, right? That's what happened there. Yeah. I think that's perfectly acceptable as long as the question allows that interpretation, right? So yeah, as you said, this asks for the minimum number of bits of storage to track this required information, and I think the quantity you computed satisfies that criteria. Yeah, I think so. This question leads you towards tracking each row state individually, right? So that's what this would be, right? 2 to the 21 times 2 to the 1, which which is, I guess, the solution that's stated in Post-only online solutions. Okay, fair. Yeah. So then part I. So this question asks to assume that the system designer now implements an approximate mechanism to reduce the refresh rate with Bloom filters. And so one Bloom filter represents all rows with 64 milliseconds, another one for all rows which require 128 milliseconds. And so we go ahead and modify the memory controller's refresh logic. So on every potential refresh of a row, so every, say, 64 milliseconds, it probes both Bloom filters, right? So both are probed for every potential refresh of a row. And so if either of the Bloom filters results in a hit, and if the row has not been refreshed in the most recent length of time for the refresh rate associated with that Bloom filter, then the row gets refreshed, right? And so if a row address hits in both, the more frequent refresh rate wins, right? So the 64 millisecond Bloom filter has priority, essentially. And so any row that does not hit in either Bloom filter is refreshed at the default rate of per 256 milliseconds, right? So we have a Bloom filter for 64 milliseconds, a Bloom filter for 128 milliseconds, and I guess the default of 256 milliseconds, right? And so we probe these two where the 64 millisecond has priority, and if neither of them are a hit, then we use the 256 millisecond quantity. So here we're provided with the false positive rates for the two Bloom filters, right? And the false positive rate is essentially if we query the Bloom filter with a particular address, what's the probability that it will tell us, that it's in that bin, even though it's not, right? And so we're saying that the distribution of row refreshes specified in part E still applies. So this table here is the same set of values that we're going to use for this part of the question. And so now it asks us to repeat the same computations, essentially, right? How many refreshes are performed during the 1024 second period across all 4 memory channels? So what we have is essentially we have these values, but we're also going to rearrange these bins a little bit based on the false positive rates, right? So for the 64 millisecond bin, we have 64 millisecond bin, and we have 2 to the 5 rows that are guaranteed to hit in the Bloom filter, right? So these 2 to the 5 rows they're true positives, essentially, right? And so we have 2 to the 5 plus the false positives, where the false positives will be essentially described by this 2 to the minus 20 quantity, right? So the probability that an address will, become a false positive is 2 to the minus 20. So we have 2 to the minus 20 times the total number of rows in the system, right? And so the total number of rows is 2 to the 21. So that is actually just 2 to the 5 plus 2, right? 2 to the 1. And so this is the number of rows that'll end up having 64 millisecond refresh because of the false positive rate. So now we consider the 128 millisecond bin. And so in the 128 millisecond bin, we have 2 to the 9 rows. We have 2 to the 9 rows, right, that fall into this bin. And then we have a different false positive rate. So we're going to have 2 to the minus 8 times 2 to the 21, which is 2 to the 9 plus 2 to the 13, right? 2 to the 13 rows. And so those will be essentially everything that's refreshed at 128 milliseconds. And then we have 256 milliseconds, which is everything else, right? And so we compute the everything else in the same way, so as we did before, right? So we have 2 to the 21 rows total, and then we just subtract these quantities, right? Minus 2 to the 9, minus 2 to the 13, minus 2 to the 5, minus 2 to the 1. Yeah? And so now we're going to go ahead and just sort of do the same thing as before, except now instead of these values as a number of rows, we have these values. And again, for simplicity, I'm going to clearly define here that this is going to be called N64, this is going to be called N128, and this is going to be called N256, right? Just to save some time here. And so we compute the number of refreshes here using the same values as here, right? So we essentially have N64 rows that get refreshed 2 to the 4 times, N128 2 to the 3 times, and N256 2 to the 2 times, right? So we just write that here. We have N64 times 2 to the 4 plus N128 times 2 to the 3 plus N256 times 2 to the 2. Yeah? So that's all that is. It's just computing a different number of rows. So then what command plus utilization results from this refresh scheme, right? So same analogous computations as before, right? So we have this quantity, which I'm going to define here, let's say as M, right? All of this stuff. And so we have M refreshes per 1024 milliseconds, right? And again, it's the same thing, right? Command bus, so we have 4 channels in the system, and then we have 5 nanoseconds per refresh, and so we end up with m times 5 nanoseconds over 1024 milliseconds times 2 to the 2, right? For data bus utilization, again, we don't touch the data bus for the scheme, so it's still 0. And for bank utilization, same sort of thing as before, right? We have m operations per 1024 milliseconds times, so here we have 2 to the 6 banks times 40 nanoseconds per refresh operation, so m times 40 nanoseconds over 1024 milliseconds times 2 to the 6, right? And so that's essentially the last part of the question. And all the comments that you guys have made throughout also apply to this part, right? So here I'm making the same assumptions that the rows are uniformly distributed throughout throughout all these different channels, and yeah, these are probabilistic arguments, right? Because depending on exactly which rows fell into here, they could potentially not be in the 128 bin, right? Because if these 2 were selected from the 2 to the 9 pool, this would actually be 2 to the 9 minus 2, right? So I'm just doing this as a general probabilistic argument, and this is fine because it's essentially, it would change very little if you were trying to compute these values. But yeah, so I think if you're ever in doubt, just state exactly what your assumptions are. And if those are reasonable assumptions and the question allows that interpretation, it should be good. Yeah. Okay, so any other questions about this? Or no? Yes.
If you enter false positive rate on key that says it's rate,
Yeah. You're saying it's that quantity, right? False positives over true negatives, as opposed to false positives over the sum of all different possibilities. Yeah. So, yeah, I think in the context of Bloom filters, we've been talking about it like this in terms of the lecture slides and in this course, essentially. So this interpretation is sort of what I just assumed. Yeah, if this is going to be your sort of pedantic interpretation of false positive rate, and you state that clearly and then solve according to that, sure, that should be fine. But we would much prefer if you use the definition we've used in the course, right? So that's what this exam is supposed to cover.
So we're going to discuss a question on memory scheduling. Let's read it first. So here. In the lectures, we introduced a variety of ways to tackle memory interference. In this problem, we will look at the blacklisting memory scheduler, BLIS, I don't know if you remember it, that reduces unfairness. And there are 2 key aspects of BLIS that you need to know. So when the memory controller services n consecutive requests from a particular application, this application is blacklisted. And this non-negative integer n is the blacklisting threshold. So when you execute n accesses or your n requests from a specific application, you will blacklist. So this blacklisting period is cleared periodically after 10,000 cycles. So every 10,000 cycles, you stop blacklisting the applications, you start the process again. So to reduce unfairness, we change the FRFCFS scheduling policy. Instead of FRFCFS, we have non-blacklisted, ready, and then FCFS. So we first prioritize the non-blacklisted applications request. So when you execute for an application, when you have 2 applications and one of them is blacklisted, then you start executing the other one until the other one is also blacklisted. So in this problem, we have a memory system that has 2 channels with 2 banks each, and table 1 and 2 show the memory request stream for two different applications in times t equals 0 and t equals 10, and for both tables a request or as we go to the right, the requests are younger. Yes, and there are not any more requests in this problem. Yes, and for each one of the requests we have information about which row in the bank it accesses. So a row buffer hit costs 100 cycles, a row buffer miss costs 200 cycles, a row buffer conflict, which means that we need to activate another row on top of another row, so we need to pre-charge first and then activate another row, is 250 cycles, and all row buffers are closed at t equals 0. So as we see in T equals 0, we have the application B, which is application B. This means that application B is the oldest one. It already has its requests in the buffers. And then at T equals 10, we have all the requests from application A arrived, but we didn't service any of these of the requests yet. So application B has not serviced any of its requests. So let's see the first question. So we need to compute the slowdown of each application using the FRF-CFS scheduling policy after both threads run to completion. And we define as a slowdown the memory latency of the application when it runs together with the other application over the memory latency of the application when it runs alone. So in this case, we need to calculate first two things. So we need to calculate application A latency when it runs alone and application B latency when it runs alone. So let's see again. So when application A runs alone, what will happen? We will execute row 3, we will perform the request to row 3, and as we see there is another request to row 3. So we can actually open this row and perform a hit to row 3 for this request that's in the back. And then we perform all the other requests. So what we do essentially is we open a row, we have a row miss, row 3, then we execute the one that I showed you in the row 3, the request, which is a hit. And then for all the other requests, which are 6, we have conflicts, right? Because they were all different. They did not have the same number anywhere. So it's 250, which is the row miss conflict, multiplied by 6, which is 1,800 cycles. So let's see application B right now. So application B is easier. So in application B, we have one row miss, and then we have 1, 2, 3, 4 hits, one conflict, one hit, and one conflict. So in this case, we have one miss, as I said. Then we have 4 hits. It was row 2. We have 4 hits. Then we have one conflict for B. Then we have one hit for 3, and then one more conflict for the last one, which is 1,200 cycles. Okay. Right now, we also need to count the memory latency of application A when we run it with B, and the memory latency of B when we run it with A, right? So let's calculate first. Actually, we will calculate them both at the same time. So it's application A when you run it with B and FRF-CFS, and application B when you run it with A with FRF-CFS. So in this case, let's see more in detail this one. It's a bit trickier. So which is the oldest request? The oldest request, nothing is open, right? So the oldest request is from application B. So application B will open this row first, right? So for sure we have in application B a miss, and application A will wait for this miss, right? So we accumulate the cycles in application A also to calculate the latency. It's the whole thing, right? The whole execution. Then application B will execute 1, 2, 3, 4 requests, because these are all hits. But there is in application A, there is also row 2, right? So we need to, before this row 3 is opened, we need to execute one hit from application A, because this request can be serviced. It's in the same row buffer, right? So we can actually perform the request. So what we will do is that we will have 200 plus 100 multiplied by 4, and 200 plus 100 multiplied by 4 because we perform an accumulative mixed latency. Then we service the row buffer, the row 2 from application A. So we have a hit in both. Then, as we see here, we need to open row 3, right? Because application B is older, so we need to open row 3. And we don't have any other ready request. So we need to pay a latency of 250. Okay. Then we need to service a request from application B, right? Because we have row 3 here and 2 row 3s in application A, but this is older. So we need to pay 100 cycles more. And then we need to service the 2 requests from application A, which are in the same row, right? It's row 3. So 100 multiplied by 2, this is application A. Then we need to service row 4 because it's the oldest one. There is no other ready request, and we need to service row 4. So to service row 4, we need to pay 250 cycles more for both. And then, how many requests are missing from application A? Because we did not execute all the applications. We execute 3, 2, and 3. So we need to service requests 7, 0, 8, 5, and 9, which are 5 requests, which are all in the different rows, which means 5 conflicts, right? So we need to perform. So application B is done because we executed all the requests from application B. So this is the total memory latency. And here we have 250 multiplied by 5. So this number is equal to 2,550 cycles, and this number is equal to 1,500 cycles. So how do we calculate the slowdown? So the slowdown of A equals 2,550 over 1,800, which is almost 1.53. How do we do that? This is the application A latency when it runs with application B over the alone execution, right? And the slowdown of B equals 1,500 over 1,200, which equals 1.15. So this is how we'll calculate the 2 latency. So, like, if there is any question in the exam like this, just be careful on 2 things. So when you run the application alone, be careful that it's FRFCFS, it's not FCFS. Like if there are 2 requests in the queue that can be in the same row, just give the hits. Do not go FCFS, because I did the same mistake when I was actually calculating this question. And second is like be careful about the common rows in the queues. Like if you see something like that, be careful that there might be the same rows across the 2 applications and service them correctly. Okay, let's see the second question. So, if we use the Bliss scheduler, which blacklists, for what values of n will the slowdowns of both applications be equal to this obtained without FRFCFS? So what we want here is the exact same slowdown, right? And we want to have this exact same slowdown. We need to have the same order of servicing the requests. So the way this can happen is twofold. So first, if we have n equals 0, then we execute the applications with FRFCFS, right? Because we don't never blacklist. So one option is to have n equals 0. So the second option, like I will do some trial and error. So if we have, let's say, 4. If we have 4, we will execute 1, 2, 3, 4. Then application A will be blacklisted. And then we need to execute 2. because this is the open one, and then 1, 2, 3. This makes application A blacklisted, and then both of them are blacklisted when you continue the execution. But this way, application B will be blacklisted, right? So it would not have the same slowdown for sure. And application A will run faster probably. So if we do 5, it's 1, 2, 3, 4, 5. Application B is blacklisted. We execute row 2, and then the same thing. So application B will be blacklisted if the threshold is below 6. So we need to at least have 6, n equals 6, because if we have n equals 6, we will do 1, 2, 3, 4, 5. We will execute this request in row 2, then 6 here, and then we do not blacklist application B because we execute a request from application A, right? So then we will open this row, row 3. We will execute something from row 3, and then nothing will be blacklisted. In this case, none of the applications will be blacklisted if we have n greater than 6, greater or equal than 6. If we have something, if we have n less than 6, then B will be blacklisted and it will not have the same slowdown. So in this case, we have two options. It's n equals 0 or n equal greater than 6. Is that clear to everyone? Yes. So, for what values of n, the blacklisting threshold, will the slowdowns of A be less than 1.5? So, do you think it's possible to have a slowdown less than 1.5 in this application?
I have a question about the last one.
Yes.
If you set n equal to 1,
to 1, yes.
I think you might be able to get like a similar result. Like, for instance, you would still blacklist B after one axis, but then you would hit A and blacklist that immediately as well, and then it would execute them as normal, like before, right?
So if you do that, you will have a row miss here, right?
But it does the row buffer hit first, right? Which means it would select row 2 from application A.
So you mean that if you have you have a conflict here,
yeah,
and then you execute row 2.
Yep. And so they would both be blacklisted at this point, and then you would go back to B because it's older, and then do all the row buffer hits, and then it would execute as previously. I think this is an edge case.
It doesn't matter. It's correct, right?
Yeah.
That's true. I think I agree with you. Yes, because we can service row 2, right? So it's the same thing essentially. Yes, I think that the slowdown will be the same. You're right. Good catch. And then equals 1. Yes, sorry. So in this case, to have a slowdown of A which is less than 1.5, we need something that blacklists B, but it does not blacklist A. Because if it blacklists A, the slowdown cannot be less than 1.5, right? But this cannot happen. Given the memory request that we have, if you see it carefully, this cannot happen. We cannot do that. We cannot have the A application running and the B application blacklisted and the A not blacklisted. So in this case, this cannot happen. This is impossible. We cannot. If you check at the patterns, it's impossible to run application A without blacklisting it and blacklisting B. If n is greater than 0, right? This is an easy question, I think. So, for what values of the blacklisting threshold will be experienced the maximum slowdown from the blacklisting scheduler? So you know that if n is greater than 6, as we discussed, or is equal to 1 or is equal to 0, then you have the same slowdown as FRFCFS. So what you would do in this question, you would brute force from n equals to 3, 4, and 5 to see what is the slowdown for each one of these numbers. So you need to brute force n equals 2, n equals 3, n equals 4, and n equals 5 to see which of these numbers give the maximum slowdown. Is this clear to everyone? So in this case it's n equals 5. So if you execute with n equals 5, then you get the maximum slowdown for application B, that is 2150 cycles. Okay, so I think this is easy. If you answer actually the question, the B, correctly, this will be really easy. And then that's the last question. What is a simple mechanism that we can use instead of Bliss to make the slowdowns of both A and B equal to 1? Does anyone have any idea of how to do that? So you want both applications to run isolated in this case. And I think you discussed it in the class. Is there any way that you can run the applications isolated?
Two channels.
How is this technique called? Okay, it's memory channel partitioning. Correct. So the technique is called MCP, memory channel partitioning. Yes, in this case we will have the two applications running in different channels, and we won't have any kind of conflicts between the banks. And it will run, the slowdown will be the same, which is 1. I think this was one of the, let's say, easy questions. But you need to be careful, like even if you don't know the Bliss scheduler, you can actually essentially solve it. It's in the example. But be careful, like this kind of stuff, with n equals 1, for example.
Is it visible? Yeah, okay. Okay, so this question actually talks about the DRAM scheduling and the latency policies. So, okay, let's read the question. So, you would like to understand the configuration of the DRAM subsystem of a computer using the reverse engineering techniques. And this is basically the set of knowledge you have from this particular DRAM subsystem. Okay, what are the knowledge? So basically, the physical address, you know that, okay, it's for 16 bits. And the DRAM subsystem consists of a single channel and a 4-bank system. And the DRAM is byte addressable. It's clearly mentioned here. And okay, the most significant 2 bits of the physical memory, it determines the bank. So you know how to decode the physical address to get the bank number. And the DRAM command bus operates at the 500 megahertz frequency. And this point basically says, okay, the memory controller issues a command to the DRAM in such a way that no command for the servicing a later request is issued before issuing a read command for the current request. So that basically says that if you have, let's say, 2 requests, which is a request A and B, and let's say A actually came first, A is the old request, so, and even if A and B are going to the 2 different banks, the memory controller does not issue an activate command to the bank that actually holds B before issuing a read command. So basically you can think of it as like a first come first serve rather than any open row policies, or it's completely oblivious to which bank you are currently, if you have a bank parallelism or not. Make sense? And yeah, and then it basically says that, okay, now you have, this is the state of the memory request that you have currently in the DRAM request buffer, and the third sequence basically says that, okay, at the same time, you take the snapshot of the request buffer and you start probing the DRAM command bus. And you observe the DRAM command type and the cycle at which this command actually issued. And the following are the DRAM commands that you are actually seeing. Make sense? And then the questions are like, okay, so it's actually asked for, let's say, the activate to read latency, activate to pre-charge latency, and the pre-charge to activate latency. So now let's see how if we know this kind of information, how we can actually reverse engineer the system and get some data out of it, right? So the first question is it's visible, right? Yeah, okay. The first question is to activate to read latency, right? So, okay. Before start using any kind of questions like this, let's first decode what the information we have currently. So we know how to get the bank information from these addresses. So let's say get the bank numbers first, okay? So this guy actually goes to bank 0100, so that means bank 01. Am I right? Yeah. So 01. So I'm just decoding the first hex digit. So the second one would be 0000. So that means the first two digits basically gives you the bank now ID. So that means this goes to bank 0. This one goes to bank 1 again. This one is bank 2. This one is bank 3. This one is bank 2 again. And this one is 1, right? So let's write it in normal form. So this is 1, this is 0, this is 1 again, this is 2, this is 3, this is 2, and this is 1. Right? So we know that which bank this request is going to. Make sense? Okay. Now we want to know, let's say, the activate to read latency. That's the first question. So let's see if we so activate to read latency is bank oblivious. So you have this activate command followed by a read command. That's there. And another pair exists here. Another pair exists here. So this is the first pair. And another pair is here. Right? So basically the activate to read latency is basically saying that you have a 4 cycle of latency. Make sense? So then the answer would be, this would be 4 cycles. Now the latency, so that means you need to convert it to a seconds format. You know that your DRAM command bus operates at 500 megahertz of frequency. That means your cycle is basically of 2 nanoseconds each. So that essentially gives you 8 nanoseconds of activate to read latency. Is it clear? Make sense? Okay. Now the second question is activate to pre-charge latency. Okay. Now let's see. Now activate to pre-charge latency, if you recollect the DRAM operation. So activate to pre-charge latency actually has to do with the DRAM row conflict. Make sense? So if you have a different open row, row open, so you need to actually close that row before opening a new row, right? So let's then focus on the accesses which are going to the same bank. Make sense? So yeah. So let's see. So this is the if we now the read accesses. The reads are the one which is actually happening to the for all of these accesses, right? So if we then simply categorize these accesses like this, so these 3 command sequences are actually happened for this access. Okay, then this command sequence is happened for the second access. Then the third 3 command sequence actually happened for the third access. These 2 is for this read. This read goes independently, this read goes independently, and then these 3 is for the last access. So this is access number 1, this is access number 2, 3, this is 4, 5, 6, and 7. Do we have 7? Yes, we have 7. Okay. So now, okay. So now the question is activate to pre-charge latency. So let's see the activate to pre-charge. Okay, now if you see, so let's say access 1 and access 3, these two accesses are going to the same bank. Make sense? So access 1 and access 3, these two are going to the same bank. So you should be actually worrying about the activate to pre-charge latency between these two cycle counts. So cycle number 6 and this is cycle number 21. Does that make sense? So that gives us a cycle difference of 15 cycles. 15 cycles translates to 30 nanoseconds. Does that make sense? Okay, yeah. There is a row conflict. So you have, okay, so these two accesses are going to the same bank, right? Now, I'm saying these two accesses are going to the same bank, but if you look at the access sequence of these two accesses, this guy is opening a new row, right? Pre-charge, activate, and read. So, yeah, go ahead.
So, just some reference maybe. So, if there are access to one bank, then that happens independent of the other bank.
That's true. That's true. Yeah. Okay.
Doesn't this really depend on how many requests in between the memory?
Okay. Okay.
Like 2 or 3 more requests, this latency would increase.
Sequence of requests is happening, but doesn't it, if you have the accesses to the same bank, it should be like the access to the different bank should not hamper the access sequence on this bank, right?
So if I had like 2 more reads in between.
Okay. Okay.
Request 1, then we have a read request, just a read command for request 2. So if I had like 2 more reads after this
Okay. Okay.
the request to some different bank, this latency would automatically increase.
Okay. That's true. That's true. Yes. Yeah, that's true. That's true. But in this case, we know that okay, these read requests actually happened in cycle 11, and before cycle 21, you don't have any other request. That's one hint you actually have, and you know that okay, request number 1 and request number 3 actually went to the same bank, right? And request number 3 actually initiated a sequence which is saying that pre-charge, activate, and read.
My point is that this is not exactly a fixed DRAM
Minimum activate to pre-charge latency, that's something we can find.
Okay.
But right now you said activate to pre-charge.
Yeah, right.
Okay, I will calculate access 3 to access 7. Both go to the same bank.
Oh, okay. I see.
100 cycles.
I see.
that it's actually every activate and read differs by 4 cycles. So there's 6 times.
That's true.
Later on there's 27, 31. So we can be sure that this is like
Okay. Yeah, I believe the question you ask is like correct. Yeah, so activate to pre-charge, whenever we are saying that activate to pre-charge latency or let's say activate to read latency, we are actually talking about the minimum time we are thinking here.
So activate to read can be minimum by itself because it's a sequence.
Makes sense. But the activate to pre-charge, it can be longer, right?
Right.
Exactly. So here what we are trying to find is basically the minimum activate to pre-charge latency. Does it make sense? Yeah.
So this question sort of, so like in this example, all activates or reads are the same length, but like homework is one that's shorter, one that's longer.
Okay.
But normally when we consider latency, don't we care most about what, like typically what takes the longest, because then we can like figure out what's
Okay.
class instead of the minimum and maximum.
Yeah, that should be the minimum one, right? Like you can wait as long as you want, right? There is no harm. But yeah, activate. So it's basically like you are trying to open a new row on the same bank, And what is the minimum time you have to wait before opening a new row?
Okay.
That defines the minimum time, right?
Yeah.
There is no harm in maximizing the time. Yeah, sure. Okay.
How it is scheduled with the cycles.
Okay.
It would have give us the minimum. Because here we don't know whether, because we are getting the request later,
Mm-hmm.
we are getting this high activate to feature, or is it because that this is the limitation?
Oh, no. So this is actually a snapshot of the events what you have. The question says that this is a snapshot of the request buffer. So it's not like that the requests are coming one by one. So the question you said, that's completely valid. If how do you know that, okay, this request actually came later, so that's why we actually issued this thing later, right? That's what you asked. But this question actually said that this is the snapshot of the request buffer at once, when you actually started seeing this. So your request buffer showed a state like this, and then you probe the command bus. That's what it says, that you probe the command bus, and you saw that, okay, this is the sequence of commands the DRAM command controller actually issued. Make sense?
What you're saying that it's like at one point of time we are getting this many requests to the same.
Yeah, no. So this means that when we actually started formulating, seeing this behavior, before this behavior, you already have this many requests inside your DRAM buffer, request buffer.
So from the scheduler point of view, it's like
Right.
at a time.
At a time, you have this thing. Now you just want to access this request one by one.
And what does that point say? For example, if there are requests A and B in the request buffer,
Mm-hmm.
is the oldest request, and two requests are two different banks.
Okay.
The
Yeah,
memory controller does not issue an activate command to the bank B.
that's right.
It's going to access the. So what does this mean here?
Here, okay. So okay, that means this thing. So let's say this is the access, and the second access actually goes to a different bank, right? So instead of, if you don't know this criteria, that memory controller actually doesn't issue any. So there is no harm in issuing the command sequence for this second access, as long as the command sequence for first access is going on, right? Because the second access is actually going to a different bank. In a real life scenario, this could have actually exploit the bank level parallelism, right?
But it's telling that does not issue an activate.
Exactly. So then it says that, okay, unless the entire command sequence for the first access ends, you cannot simply issue any command sequence for the second access. That gives you a deterministic behavior, how you can actually categorize this access sequence for the particular request.
So if we have like multiple banks, multiple requests to a different bank,
Okay.
then in that case, this
It's just a,
schedule level means the scheduling will be different. In that case, if we are calculating some activity, then it will be even higher, right? Because in that case, what we are doing, unless the first, according to
okay.
this thing is completed, we can't send a request for other banks.
I see your point. So you are saying, okay, it might get serialized just because of that reason.
So it might add additional
Okay.
cycles, and the things we are calculating for activated features might not be
The lowest one. Okay.
So if there are like after bank one, we are scheduling bank one,
Mm-hmm.
but we have access to a different row, then calculating.
Does make sense. Okay. So I would suggest, okay, this question is kind of going towards a straightforward notion of, let's say, categorizing the command sequences to map which access request it's actually serving. Okay. So now you can think of it like this. So cycle 11, and then there is nothing happening between cycle 11 and 21. So that means if all of these accesses are actually happened all at once, then there is some timing constraint which is hampering this thing to go forward. Make sense? So that's how we are calculating. Okay, then 6 to 21 is the minimum. You have to wait, and then you have to go on. Okay. So then 6 to 21, if you want to verify this, with something else, you can also see that, okay, this timing constraint actually holds for other remaining access also. So, okay, the second one is precharge, third one is precharge to activate latency. Okay, now see. So, yeah, precharge to activate is straightforward. So, precharge to activate, and then precharge to activate. In all three cases, both these three pairs actually followed by 6 cycles, right? So that means it has to be 6 cycles, which is equivalent to 12 nanoseconds. Make sense? Okay. Now, a little bit trickier question. So what is the row size in bytes? And explain your answer. So, okay, to approach this question, I would say that you should first think of, let's say, a row buffer hit would actually give you an idea how big is the row buffer, and a row buffer miss will also give you an idea how big is your row buffer. Make sense? So first approach would be to first figure out which accesses are actually going to the same bank. So that gives you the first access, the third access, and the last access. This is one candidate, these 3. Make sense? And these 2 are the another candidate. You can extract your information from these accesses. Does it make sense? Okay. Now let's see. Let's see how big is the row buffer, right? So let's see the first sequence of accesses. So 4C80 and then 4EC0, these 2, and the last one, 4E80. Okay? So let's see. 4C80 actually serviced by these 3 command sequence. The next one, the 4EC0, is serviced by these 3 command sequence. Now, if 4EC0 is actually getting serviced by precharge, so that means 4C80 and 4EC0 are not on the same row. That's one hint. Second hint, 4E80, this guy, and 4EC0, the last access to the same bank, it's also getting followed by the same precharge. So that means these 2 are also not on the same bank, same row. Does that make sense? Okay. Now we see that, okay, okay. So these two are basically 800 and 803F. So let's see. Oh, am I making some mistake? No, okay. So 800 is this guy, and 803F is this guy. So now if you see the access number, this access 803F, last by 1. So last but 1, this access is actually just a read sequence. So that means it's actually hit in the row buffer, right? So these actually gives us an idea that, okay, for 8000 and 803F, these 2 accesses belong to the same row, but the minimum one is basically 4E80 and 4EC0 actually belong to the different line. Now, what's the minimum size then? Like, which size of the row buffer will actually satisfy both of these constraints, right? So let's see. If we just decode the last 2 hexadecimal bytes, it's basically 0000. This is 1, and this sequence would be 0011, 1111. So that gives us this boundary, right? Okay. Now another one would be wait. This is what? 0800. Okay, so 1000, 0000, and C is this. Can you see can you identify the boundary of the row buffer? So it basically says that, okay, if these 2 address values are belonging to the same row, but these two address values are belonging to the different row. So that means your row size would have at least these many bytes inside a row. How many bytes of that? So you have 6 bits of addresses, 6 bits translates. So this is an byte addressable memory. 6 bits translates to 64 byte. Make sense? So that means your row buffer size would be of 64 byte. Is it clear? Okay. Okay, now let's go to the second question. Third question basically. Okay, so let's read the question. What is the status of the bank prior to the execution of any of the above requests? So these are the request sequence. Before this request sequence even happened to the DRAM, what is the state of the DRAM? It's asking for that question, okay? So in other words, which rows from which banks were open immediately prior to issuing the DRAM commands listed above? Fill in the table with below indicating whether the bank has an open row. If there is an open row, specify its addresses. If there is not enough information, just simply say unknown, okay? Let's see. So now, let's say open and closed. So your accesses to the access sequence that you are actually generating for a request will give you the information of the prior state of that bank. Does it make sense? Okay. So now let's see. So bank 0. So which access actually went to bank 0? This is the one which went to bank 0. The second access. What's the second access command sequence? Second access command sequence is this one. That's just a read. That indicates there is an already same row which is happening on the same bank, right? So that means, okay, the first question is open or closed. It's definitely open. That's why you actually hit that row. Make sense? Okay. Let's see now, so which row address is then open? Now, if you see this, so you have 16 bits of addresses. You know last 6 bits are basically the row address. So that means if you simply chop it off, so these 6 bits are actually going for the row offset. These 2 bits are actually going for the bank number. The remaining 8 bits is basically giving you the, am I right? Yeah. It's giving you the row number, right? So now if you simply calculate this, so let's say bank 0. So bank 0 means this access is what? 0140. So 0001. 0001. Sorry? Oh, I'm sorry. Okay. So 4 means 0100 and 0000. Right? So if we truncate this, this is the 8-bit sequence you are left of. So this is 0 and this is what? This is 5. So that means 0 and that's 5. Does that make sense? Is it clear? Yeah.
Is it not also acceptable to write the memory address of the first addressable?
Well, yes. Okay, you're right. I think so. Yeah. So then it should be then it should be 0 0 0 0 0 0 0 1. You know how to do this. So it's basically this is the first address basically. Yeah. This is the first address. Does it make sense? But this is how you should actually approach the question. Like, the open row address would be the first row address, I guess. This portion will be anyway 0 for the first address. Make sense? Okay. Now let's go to the second bank. Okay, bank 1. So which accesses are actually happening to bank 1? Bank 1, these 3 accesses, right? The first access to the bank 1 is 4C80. 4C80, the first access started with the pre-charge thing. So that means, yes, this is open. Now, which one was before? Before this thing? Exactly. So we don't know this. Make sense? Okay. Let's go to bank 2. Now bank 2, this is the one, this is the one. So this is the 4th access. So let's say fourth access is this one. Fourth access basically says that activate and read. On what condition we have activate and read? We have a closed row, right? So that means bank 2 is already closed, and then there is nothing open here. Okay, fine. Now let's go to bank 3. Bank 3, the only access to bank 3 is this guy, the third last. Third last is this guy. So this is actually just a read command. So that means whatever you are accessing, it's hitting the row. You know how to, then this is definitely open, and using the same tactics, we can actually get the address of the open row. Make sense? Okay. Now comes the trickiest part of the question. So, okay, this question basically talks about the DRAM architecture. You probably have gone through the DRAM architecture, right? So it basically says that to improve the performance, you decide to implement the tiered latency DRAM. Now, assume that the bank consists of a single subarray. With DRAM, an entire bank is divided into a near segment and the fast segment. When accessing a row to the near segment, the activate to read latency reduces by 2 cycles, and the activate to pre-charge latency reduces by 5 cycles. Whereas when you're accessing the fast segment, activate to read latency increases by 1, and activate to pre-charge latency increases by 2. Fine. Now, this also says that, okay, let's just consider the near segment have the smaller row IDs. Just the first row ID basically belongs to the near segment, and the fast segment will have the higher row IDs. So basically 0 to n-1 belongs to the near segment row IDs, and n to m-1 is the fast segment rows. Okay? Now the question is, if the above DRAM commands are issued 5 cycles faster than the DRAM, faster with DRAM as compared to the baseline, so that means it basically says that it previously it ended in 52. Now what if it actually ends in 47? And then the question is, if it actually ends 5 cycles faster, then how many rows you have in the near segment? That's kind of a very neat reverse engineering. Okay, so let's start with the let's say how to approach this problem in the beginning. So you have the activate to read latency and the activate to pre-charge latency. So it has something to do with the activate commands and how far the read and the pre-charge commands are apart from the activate. So let's target the activate first, and let's see which rows it's actually using, which bank it's actually using. Okay, so I'm going to write this again for this thing. Okay. Okay, now let's see. Can I show this side by side? Yeah, that's possible. Okay. Okay. So now if we see, so let's say this is a pre-charge, activate, and the read command, right? So let's see, this activate is happening to which bank and which row. Okay. So this activate is definitely for this guy, right? So this is bank number 1 and row number. Yeah, we need to calculate the row. I guess I have the row calculated somewhere. Okay, so this is row number 50, just for fasting. Okay, so this is just a read command for the second guy. So let's not consider that for now, because these guys are anyway not creating any activity request, so we might not consider it for now. Okay, so let's see. The second, the third access also comes with the 3 issue sequence: activate, we have a pre-charge, activate, and read. So let's see. This guy is also to bank 1. This is row 59. I know this. Okay. So now this is an activate to read. This guy is for bank 2. And this is for row what? I believe it's 0. Yeah. This guy is again a hit, so we are not considering it for now. This guy is again a hit. We are not considering it for now. This guy is another guy which has an activate. So let's see. This is bank 1. This is row 58. Okay. Now what we need to see is basically we know what information. We know what is the latency sensitivity of the fast segment and the near segment. That's one thing. That's one information we know. And the second thing we know that, okay, these are the accesses which generated an activate request, and these accesses are actually happening to this bank and this row. Okay? Just by seeing this, you can probably get an idea that it might be somewhere between 58 or 59 or maybe 50. That's just a hunch. Okay? Now, let's start. I would say I would approach like this. So let's start with saying that, okay, row 50 is something we are considering to be a near segment. And let's say 59 and 58, both of them to be a fast segment. And let's see how the command sequence looks like. What the timing parameter actually looks like. If it doesn't match, we'll go back and we'll say that, okay, let's make 58 also as a part of near segment, not a fast segment. Okay? If it doesn't match also, then we'll go back and consider that 559, consider it also as a near segment. Yeah.
Considering the row address are like properly
That's what this line says, that, okay, you can consider 0 to n-1, the first few rows to be the near segment, and the remaining rows to be the fast segment. Make sense? Okay. Now, let's see. So if we consider, let's say, can I show this side by side? Let's say, okay, let's show this like this. It's visible? Okay. So if we consider, let's say, 50 to be the near segment, and 58 and 59 to be the fast segment. So basically 0 and 50 goes to the near segment, and 58 and 59 goes to the fast segment. Okay? Let's start with this one. So what we have the changes in the activate to read and the activate to precharge. So there is nothing for precharge to activate, right? Precharge to activate is same for everyone, right? So let's see. 0, 6. That's like the normal sequence. Okay? Now activate to read. Activate to read is basically, it was before 4 cycles. Now you know that if it is near segment, then it will reduce by 2 cycles. So that means later on it will come as 8. Okay? So now let's see. This guy is just a normal read. So it can simply go on the next cycle. So that's 9. Maybe it's a better idea to put it like this. Okay. And then see, precharge. So then activate to precharge is one dependency. If we know that, okay, this row is a near segment, if we have considered that as a near segment, so that actually gives you a 5-cycle benefit of activate to precharge, right? So previously activate to precharge, so this activate to precharge was 15 cycles, now it actually becomes 10 cycles. Just stop me whenever you can get the flow. Sorry? Right. So okay, the question is to get the boundary, right? We need to get the boundary. Now, we should start from some place. Let's consider 50 as a boundary. So I'm considering 50 for now. I'm considering 50 as a boundary. So anything from row 0 to 50 actually falls to the near segment. Anything from 51 and upwards is basically fast segment. Okay? So near segment, any access to the near segment comes with 2 benefits, activate to precharge and activate to read. Some cycle savings, okay? Anything on the fast segment, which I considered this one and this one, is coming with a penalty, some access penalty. Make sense? So right now, I'm just trying to figure out whether my intuition is correct by getting the timeline. If my timeline doesn't match with this constraint that, okay, you have 5 cycles faster, then I will roll back and go and consider some other row to be the boundary. Does that make sense? Okay. So, and I'm just considering reconstructing my timeline based on these assumptions. Okay? So, okay. We are at here. So this is the precharge. Now, this is the precharge. So this precharge is happening to the same bank. This is correspond to this axis, happening to the same bank. But now you need to close this guy. That's the near segment we have considered. So we will actually get a 5-cycle benefit. So that means now, earlier what 6 and this was happening at 21 because you had to maintain a 15 cycle gap. Now you can actually get it done at 16. Does that make sense? Okay. So now if you can get it done at 16, then pre-charge to activate, it's always same. There is no benefit in TLDRAM. So this timeline actually went to 22. That's 6 cycles, right? And then activate to read. Now consider this. So currently now you are at R59. R59 is a fast segment. So your activate to read will actually get penalized by how many cycles? Activate to read is increasing by 1 cycle. Make sense? So now your activate to read, previously it was at 4 cycle latency. Now you had to charge 5 cycle. So now this thing will actually come to 27. Yeah, go ahead. Right.
But there were different rows, so we get no benefits and no penalties.
Pre-charge to activate.
Yeah, we pre-charge the row 50.
Right.
Yeah. And then we activate the row 59, but there are different tiers, so we just
Yes. We don't actually have any benefits on the, at least according to the description, we don't have any benefits for pre-charge to activate.
And if we did, for example, hypothetically have it for our segment, for example, but this was pre-charged in the near segment and activated in the power segment.
No. Then it will be mentioned clearly that what. So if you're pre-charging a near segment and then activating a fast segment, all like that. Make sense? Exactly. All those combinations will be there. Make sense? Okay. Now let's move on. So this is the read request. So we have actually done. Okay, the read request is done. Now let's see. This is the activate request. This is the fourth request. Fourth request is going to bank 2, which is completely independent. So we can simply issue it on 28. I'm so sorry. Okay. So this is happening at 28. Okay. Now this is another activate, right? So we have considered that this R0 actually falls into the near segment. So activate to read is reducing by 2. So that means it's actually coming, this 36 is coming to 30. Make sense? Okay. Now let's see. Now this read is completely independent. So this can go and 31. Okay. And let's see. This is another read which is also happening on the same 6 mins. Whoa. Access number 6 means this. This is the second 2. So this is happening at 32. Okay. Now let's see. This is a pre-charge. So this pre-charge will actually happening on the bank 1. Okay. So bank 1. Previously we have access bank 1 in the access number 3, request number 3, right? So this activate actually happened in 22, right? So now we need to check the activate to pre-charge latency. So there is a constraint. We have mentioned the constraint, right? So now when we have considered that, okay, row 59 was in a fast segment, so activate to pre-charge latency will get increased by activate to pre-charge by 2 cycles. So which it was as 15 cycles, now it will become a 17 cycle. Does it make sense? Right. So then we are just simply charging a 17 cycles for this guy. So that comes to 49. Am I right? Oh, sorry. Yeah, I think so. Okay. So now see. Now let's see. Okay. Now pre-charge to activate, it's 6 cycles. Okay. So I'm already passing. Did I do something wrong? Which one?
You added 17 to 32, which is not.
Which one?
You added your activated pre-charge latency to.
Oh, I'm sorry. I'm so sorry. Okay. So this should be 22 to 17, right? This one is 22. So 22 plus 17 should be, okay? Yeah, I actually added from 32. So this should be 22 plus 17, 39. Does it make sense? Okay. Oh, thank God. Okay. So this is 39. And then, so pre-charge to activate is basically then 6 cycles more. That's like 4, let me just put it this way. This is 45. Now activate to read. Now the activate to read, if this R58 actually, so we started with R58 as a fast segment, right? If this guy is a fast segment, that means activate to read, which used to be like 4 cycles, it has to be now 5 cycles, but you know that 5 cycles will overshoot. Then let's just consider this guy to be near segment. If we consider this guy to be near segment, that gives you 2 cycles benefit. So that means you can actually get it done by 47 cycles, which is like 52. Everything matches, you're happy. That's it. Okay? So I would say the approach would be just to, like, when you know that, okay, this is 50, 59, and 58, you know, consider some boundary, go with the timeline. If it doesn't match, then consider another boundary. Just like a normal search or binary search, whichever works for you. Yeah, go ahead.
Would it be possible to get a problem where the boundary is somewhere in the middle, like 80, you know, it's 85 is
Mm-hmm.
in the near segment, we have an idea it's somewhere in the middle. Here is 85
Okay.
was the far segment for us.
Okay. Okay.
Figure out that's the solution. And
Okay.
50 is the near segment.
Okay.
We technically can't know the boundary.
I see. No. So the,
Will you tell us that you have to give you a number, or you have to give an upper bound or lower bound?
okay. So if I would say the question would be deterministically answerable. If it is not deterministically answerable, then we are expecting some bounds. If it is not, then we are expecting a correct number. For this case, let's say you know for sure that, okay, if you consider 58 to be on that side, on the fast segment side, you are not matching the timeline. So that means 58 has to be on the near segment. And then you know that, okay, there is another guy with 59. So that means 0 to 58, 59 rows are actually in the near segment. But what if you don't have 59? Then you don't know actually the boundary, right? Then we are expecting not an exact answer, but as a bound. Make sense?
Say at least 0.
At least, yeah. But for this question, it's completely definite that 58 is a boundary. Make sense? Okay, fine. Yeah, that ends my session.
Which is in the, which was the first question of the last final exam. Let's first read the problem. So researchers at Lindenthal developed a new memory technology called LM, which is non-volatile. The access latency of LM is close to that of DRAM, while it provides higher density compared to the latest DRAM technology. And LM has one shortcoming, however. It has limited endurance, i.e., memory cell stops functioning after million writes are performed to the cell. So it means that a memory cell cannot store reliably the requested data. So actually we can try to write a data, but it does not guarantee the let's say the lifetime or reliably stored in time for the request. So this is, let's say this is P, which is program cycles that allowed for a cell. And the first question is asking, let's read the first question. Lindenthal markets a new computer system with LM to have a lifetime of 2 years and the following specifications. Okay, so their target lifetime is 2 years. 4 gigabytes of LM as main memory with a perfect reliable mechanism. Somehow they can provide a perfect reliability. It means that even if we try to write a data on a very specific location, the memory devices somehow distribute the requests, evenly distribute the request to the underlying cells. So so this assumption allows us to forget about the access pattern of some programs. Okay, so this value is also important. this is capacity. Let me put this as C. Yeah, C is 4 gigabytes. It means 2 to 32 bytes. Okay. Yeah, and the processor is in order and there is no memory level parallelism. It means that we cannot, with the system, we cannot overlap the latency of the device. And it takes 4 nanoseconds to send the memory request from the processor to the memory controller, and it takes 20 nanoseconds to send the request from the memory controller to LM. The write latency of LM is 40 nanoseconds. So to write a data to LM cell, it takes, the total time is, let me put this as T write is T transfer time from the processor to memory controller. Let's put this T PC PM, and another transfer from memory controller to LM, and the program latency of LM, and it's 64, right? nanoseconds. And LM is word addressable, thus each write requires the size 8 bytes to memory. So there is another important value here. I will put this as S. The size of a request is 8 bytes, means 2 to 3 bytes. Okay. The final question is, an ETH student tests the lifetime of the system and finds that this new computer system cannot guarantee a lifetime of 2 years. So she writes a program to wear out the entire LM device as quickly as possible. And it is finally asking how fast she is able to wear out the device. It means that actually this is the guaranteed lifetime at the worst case, right? So I will put this as T. So to calculate T, we can simply calculate the T by multiplying the number of write requests necessary to wear out this entire LM device. And since there is no parallelism, or there is no way for us to overlap the latency, so we can simply multiply the time for handling a write request is T right? And the number of write requests required to wear out entire LM. Let's first think about how many write requests is necessary to write hold the device at just one time. Then, we need to fill the data for the entire capacity. So let's first use the terminology C, and we can write as large as the size S. So the total number of write requests should be C over S. And we repeat this write request for the limited program cycle of a cell, right? So our final formula should be like this. Is it clear? Okay. Yes. So only the simple calculation is left here. like this. And let me check so we are doing right thing here. So this C, the unit of C is byte, right? And this size is also byte. And there is no unit for P because it's just the number of times. And this is second, right? Yeah, so we are now calculating the time for time necessary to wear out the entire device. So you can just cancel this and cancel this. Like this, and okay, somebody okay, so we can so the final form, is it okay to put just this value for the final answer for this question? And as I remember, this is just 300 something days. So it cannot guarantee the target lifetime at all. Can I move on? So we need to improve the lifetime, the guaranteed lifetime of this device. And here is another information. LRAM works in the multi-level cell mode, in which each memory cell stores 2 bits. As we have learned in the lecture, by putting some distinguished different states, so making some distinguished states for a cell, we can a cell can represent multiple bit value. For example, if we store 2 bit values for a cell, we need to make 4 different states by using a cell. And students decide to improve the lifetime of LM cells by using the single level cell SLC mode. So in part A, so a cell stores 2 bits, but in part B, we change the cell to store just 1 bit value. It means that our capacity of SLC LM device is half of NLC device, right? And when LM is used in SLC mode, the lifetime of each cell improves by a factor of 10. It means the limited program cycle of SLC is 10 times of that of MLC device. And the write latency decrease by 75%. So we should careful for this, because we use T write MLC. It means the time required to write a data to a word to the LM device, but it consists of the transfer time from processor to memory controller, and transfer time from memory controller to LM, and the write latency over LM. So this 75% reduction is only for this. So record the value. So this was it. This was what it was, and so so effective write latency over SLC, it should be like this. Right? And is 34. And what is the lifetime of the system using SLC mode if we repeat the experiment in part A with all else remaining the same in the system? And so again, we need to calculate the lifetime of this LM when it is used in SLC mode. And we can use the same formula here. And actually SLC, so the request size is not changed. So we can use the same value for this, and capacity SLC, limited programming cycle of SLC, and T right for SLC, and yes, and let's say, okay, so this should be same as MLC, and the capacity is reduced by half, and the program cycle is increased 10 times. And this is quite tricky. And you can use like this, right? Yeah, so we know this value, was, So actually, you can. The only thing left is just to simplify this final formula. Let's see. So this means, by using LM device as a SLC device, we can improve. The improvement gain is about less than 3x, right? So as I remember, this is about 1000x, x days. And the final form, should be, you don't need to calculate the exact number of this. Is it clear or clear? So it can. So it means that finally it meets the target lifetime of the device, but it does not mean that there is no problem now, because we reduce the capacity of the main memory system. So there should be some drawback of this approach, because the total capacity of memory system is decreased, so there should be more, it incurs more IOs, page faults in these systems. So even if we are, so the access latency is also decreased, but we cannot guarantee that the performance of this memory system is improved by using SLC device. Okay, the final question is, provide a mechanism that would increase the guaranteed lifetime of the computer system without changing the physical circuitry of LM. From the baseline computer system in part A, describe the changes required to guarantee a computer system lifetime of 2 years with your mechanism. Okay, so again, the guaranteed lifetime should be capacity. So capacity over request size, and in this system, and program cycle, limited program cycles, and effective write latency. And effective write latency is composed of processor to memory controller transfer time, and memory controller to LM transfer time, and the program latency of LM. So we cannot change any circuitry of LM. So we cannot. So there are a lot of ways to improve the lifetime. So, for example, we can improve the lifetime by improving the capacity, or limited programming cycles, or reducing the size. But it also affects each other's value. So it is not quite straightforward. But the assumption is we cannot change any circuitry of LM. So we cannot change the capacity first, and size also, request size also, and the program cycle. So the only thing, and also the program latency. So only thing we can change is just transfer time between processor and memory controller, or from memory controller to LM. So, and this lifetime should be more than, let's say, more than 2 years. And capacity is not changed, and size also not changed, and limited program cycle is not also changed. So this, and let's say this. Okay, and this is also not changed, for example. So in this example, it was 40 nanosecond, and we can only change these two values, and I'll put this as X. And we needed to increase this transfer time between the process and process to the memory to satisfy this inequality. So this, I think, it is sufficient to just minimize this formula. And 2 years is second, right? And like this, and it, as far as I remember, is about 50 nanosecond. Is it clear? It is not very good approach because we will not use the potential performance of LM. But if our most important concern is to guarantee the lifetime, we can say this approach as a throttling, and it is commonly used when we design real systems. And the required value, so the delay value is 40. So actually our original transfer time was 24 nanosecond total. So we double the transfer time just for guaranteeing the lifetime of the device, 2 years. Okay, it's all. So any questions for this? Thank you.
Probably you will need first to be reminded of the question. It was like part of homework too, which was a few weeks ago. Probably you forgot the questions that were here. But this question is basically about main memory and its organization. Right, so here at the beginning, it gives you a small piece of code, which is a simple array traversal. It goes through all elements of an 2-dimensional 8x8 array and sums up all elements right here in this line. So here this question uses kind of weird terminology. So it says 8-way interleaved memory. So here it really means banks, as it is like clear here in this picture. So it is named as from bank 7 to bank 0. And it is byte addressable memory, which is like another important thing that it gives you. The total size of memory is 4 kilobytes. And those elements of the array are two-dimensional. Each element is 4 bytes in size and stored in memory in column major order. So which means, so in row major order, elements of a row are in consecutive memory addresses, right? So in column order, it's vice versa. Elements in the same column are in contiguous locations in the memory. So basically, this means since this inner loop iterates over the row elements first, you have some accesses that are like spread, that have some strides in between, right? So you're not accessing, when traversing this, you're not accessing elements contiguously, right? But you're like jumping to different addresses by some stride. Okay, and the width of the memory bus is 32 bits, 4 bytes, and each memory access takes 10 cycles. So those are all information provided in the text, but there's also some information here in this picture that you will need to take into account. Okay, so the first question is, since the address space of the memory is 4 kilobytes, 12 bits are needed to uniquely identify each memory location, like each byte, right, because we are addressing bytes here, and specify which bits of the address will be used for what. And here you have some space that you need to fill. So here, byte on the bus. So the bus was 32 bits, right? So it is 4 bytes. To address 4 bytes, you will need 2 bits, right? So where those 2 bits should be in a $12-bit address. So this is 12 bits. So this is the entire address where those 2 bits should be placed. Right, so if you look at this picture here in the down part, it shows the how data is organized within the chips of the DRAM, right? So this is a picture of a single bank, of bank 0, of rank 0. And here you can see that bytes of elements are spread to different chips. Right, so here, A00's lower bits are in this chip, then the next 8 bits are on next chip, and so on. So that means first thing you interleave in your address are the bytes. Right, so you can infer this from this information by looking where bytes of the elements are placed inside the chips. Okay, so we know that this is like 2 bits, and this should be the first 2 bits of an address. So here what we need to fill is 1 to 0, right? And then the next thing that we need to fill is interleave or bank bits. Again, we look at this picture, and we see that elements inside a row are mapped to the same bank, right? So A00 is here, and A01 is on the next row of a bank. And the elements of columns are in different banks. Right, so we have 8 banks in total. It says 8-way interleaved, so we need 3 bits. Where those 3 bits need to be? So we access in. It is stored in memory in column major order, right? So if it's stored in memory in column major order, then those are supposed to be consecutive bits, right? So the element in the next column, next element in the same column is supposed to be in consecutive memory addresses. That means the first thing that needs to come after the byte address should be the bank address, right? So we know it is 3 bits, and it should come after the byte address. So it will be from 2 to 4. It's the bank address. Is that clear? Because it is kind of tricky to think about, but yeah. So basically, you look here. The next element is here, and this needs to be in consecutive addresses, right? So this needs to be then the bank address, the next thing to come in the 12-bit address bits. Okay. And then chip address. So this is, again, kind of like odd terminology that we, I think, never used in the class. So here by chip address, it means actually the raw address, right? Address inside the chip. So we can maybe correct this as a raw address. So you know all chips operate in lockstep, right? So you don't have individual access to the chips unless they are in different ranks. Okay, so this is row address, what is meant here. And so we know how many rows we have from this picture, right? So it has put here dots, but we know that if you look here, the elements from 0 to 7 come here. So this means we have 8 rows in total. So again, we need 3 bits to specify the row address. And the row bits needs to be, again, the next thing that comes, basically the bits after 4th bit. And the reason for this is basically, again, how the elements are laid out, right? So, so this is rank 0, right? And all the data, the entire array, A by array, is mapped to rank 0, right? And those are consecutive addresses. So if we switch the rank, if we put rank bits as the next thing, then the data should have been in the next rank. But here in this picture, we see that it's only on the rank 0. So the next thing to come is the row address. And again, here from the elements, here we see that it's on the next rows. So we write here from 5 to 7, right, 3 bits. And then the rest is rank bits from 8 to 11. And then we can tell also how many ranks we have right after this. And you can also tell it by looking at the size of the memory it is giving us, 4 kilobytes. Okay. Any question about this? Anything that's not clear? Okay, so you have probably checked the solution already, but sometimes the solution is not that clear. So it's good to iterate over it. Okay, the next question, it's on this side. How many cycles are spent accessing memory during the execution of the above code? Compared with the number of memory access it could take if the memory were not interleaved, single 4-byte wide array. So this means if you have just a single bank and you don't have ranks, I suppose. But ranks are not used anyway. Okay. So let's first calculate how many cycles it will take. So each access to the memory is 10 cycles. If you have multiple banks, if you access multiple banks, this means you can overlap some of the latency of the accesses, right? But here in this case, if you look at it, so the elements are accessed in row major order. So data is placed to the RAM, to the memory in column major order, but the accesses are in row major order. So you first access this element, then this element, then this element. So you have conflicts in a bank, right? So you interfere for the same bank, always. Almost always. So if you look at the inner loop, so you access the same bank, you access the bank 0 8 times, and then when switching to the next iteration, so once we finish the inner loop once, and then go to the outer loop, and then get into this again, we switch to the next bank, right? So we have a little bit overlap here when we switch to the other bank. And basically, how many times we have this overlap? It is 8 times, right? Because we actually it's 7 times because we don't have anything to overlap with in the last outer loop iteration. So it is basically we have, just to like visually represent the pattern we have here, I will use this notation. So C for conflict, right? So we make the first access as C. We don't have anything to overlap with it because it's the first access. So I'm like here noting the accesses during the execution of this code here. So when accessing the first element, we go to bank 0, or maybe it's better just to write the bank number. Okay, so we go to bank 0. We go to bank 0 8 times, right? Okay, I'll just write it. So this is 8, and then we switch to bank 1. So here we have some overlap, right? So each of those took 10 cycles to complete, each of those zeros. But here we can overlap. So it's part of this access comes for free, right? So we can overlap it with the previous 10 cycles access. And then we continue to access 1 and then switch to 2. So if you consider this pattern, you will see that those overlaps happen 7 times because in the last iteration, we don't have anything to overlap it, right? So we here somewhere we end with 6, then comes 7, and this is the last thing that we can overlap. Okay, and basically to calculate how many cycles it will require is, and you can also like count it since the array the array size is very small. One option is to count it, but you can also formalize it. And here the formula, the easier way of calculating this will be assuming all accesses happen. Okay, I'll just write it here. So we have 8 by 8 accesses, right? We are accessing in total 64 elements, and each of those will take 10 cycles if all of those were bank conflicts, right? So this is actually the other case, a single 4-byte wide array case, right? And you can calculate how many cycles this is. So this is 640 cycles. Okay, but since we have some overlap in latency, we need to like subtract this latency, subtract the overlap. So here we have 9 cycles overlap, right? Basically, after issuing a request to bank 0, in the next cycle, we can issue a request to bank 1, where the request to bank 1 will complete 1 cycle after completing the request to bank 0. Right, so we'll have only 1 additional cycle. So we'll need to subtract 7 by 9 from this, right? And the result is basically 640 minus 63. That is 7. Is that correct? Yeah. Cycles. So this is the case, the number of cycles this program takes to execute on an 8-bank memory system. If you had only 1 bank, it should have been slightly more. Yeah. Okay, I'm going to the next one, if there are not any questions about this. Could you press the button while talking? It's good to have it in the recordings. Yeah. Is it working? I think you need to press it hard. Oh, it's not working? Okay, okay. I mean, it's not convenient. Okay, yeah. Yep. Is it? Yeah. I mean, there are still rows here, right? So the first thing is row, but it indicates the row number, right? So this guy here, this is the row number. So it's also same in the picture, right? So this is the row number. So this is like A10 means the first element of the second row, right? So this is row 0, this is row 1, and this is the element that is referenced here.
But if it is column major,
Yeah.
shouldn't the column be the same back?
So elements of columns. So, okay, let's read the question again. So it says here that are 4 bytes in length, elements of array A are 4 bytes in length and are stored in memory in column major order. So in row major order, you store elements of rows in consecutive addresses. So it says the elements of columns are stored in consecutive addresses. So this is the information that is given to you. And then we filled those numbers here based on that information. Okay, I think I'm going to the next one. Can a change be made to the current interleaving scheme to optimize the number of cycles spent accessing the memory? So here what we did wrong was, by saying wrong, I mean the reason why it took too many cycles was basically because we laid out the array in memory in a way that is not efficient to access, right? So we stored the array in column major order, but we were accessing it in row major order, which caused those conflicts, those bank conflicts. So what we can change in the scheme to solve this problem is basically to replace bank bits and row bits, right? So if we change those, so if we put here so both are 3 bits, so if we do this 7 to 5 and do this 4 to 2, then the problem is solved, right? So by accessing this array, we will first access different banks. We will go to different banks for consecutive elements in row major order. And then, and then switch to the next row. Basically, we'll have a lot of parallelism, bank level parallelism. Okay. If yes, which bits of the address is used to specify byte on the bus interleaving and blah, blah, blah. So basically, we already did that. So those byte on bus stay same, rank bits stay same, and we only switch chip address or row address and bank bits. Okay, with the new interleaving scheme, how many cycles are spent accessing the memory? Remember, the elements of array will be still stored in column major order. Okay. So basically, what has changed is now in this pattern, it will be like this, right? So instead of like 8 zeros, here we will interleave between the banks 1 to 3 to 7, right, and then go to 1. So since we have 8 banks and the latency is 10 cycles, we may not be able to like overlap some of the latency, right? But so let's like calculate it to see what happens exactly. So I will draw this like this. So here at this point, this is time 0. We start the first access, and it takes 10 cycles. Right? It completes at time 10. And then on the next cycle, we can start the access to the next element. It will complete in 11. And so basically this continues like this, and the access to the last bank will be started on cycle 7, right? And it will complete on cycle 17. So we will have this this pattern continuously. So here on cycle 7, on cycle 8, we will again want to access bank 0, right? But at cycle 8, this bank 0 is still busy. It is servicing the previous request. So this will need to wait till this point, right? So basically, each iteration of the inner loop will take 17 cycles. I'm sorry, it will take 10 cycles, right? So it will take this much each iteration, plus in the last iteration, we will need to wait for the last access to complete, which will add another 7 cycles. So basically, it will be 8. We have 8 outer loop iterations by 10 cycles, multiplied by 10 cycles, plus 7 cycles for the completion of the last access in the last iteration. And this is 78 cycles in total. Right. So just by changing the interleaving scheme, we have improved the execution time of this program significantly. Okay, and D is very similar to this, but the difference is that instead of like changing the interleaving scheme, it asks what kind of optimization we can make to the program to achieve better performance. So this is like something that you have probably taken into account when writing your programs. You are trying to access your arrays in row major order because you know that the array that you have allocated is stored in row major order in memory in your system. So you try to write the program, if possible, in that way. So this is, again, like a similar thing. So here, since the array is allocated in column major order in the memory, if you access it in column major order, again, you will achieve the same effect of changing the interleaving scheme on the addresses. So what we need to change in the code is basically, since it won't change the result, we can replace I with J and J with I, basically swap the iterators here, right? And then it will be exactly the same as changing the interleaving scheme, and we will achieve the same performance. So here the answer to how many cycles are spent accessing the memory will be the same, 87 cycles again, right?
The next problem is the Potpourri about main memory. So as it says a machine has 4 kilobyte DRAM main memory system. Each row is refreshed every 64 milliseconds. And it's important when you solve or when you read this solution, it's important to keep in mind this note. It says this is an open-ended question. So there might be many different ways of answering this question. When we grade your answer, we will take that in mind. So we will consider probably any answer that you might give. It's going to be good or it's going to be interesting. These are just some possible answers. It's important to keep in mind that for these answers in this question, so the answer that you have here in this solution, we are going to consider that this memory or the memory scheduler uses first ready, first come, first serve policy. And so the answers that you can read here are given assuming this scheduling policy. So part A says the machine's designer runs 2 applications A and B on the machine. Although applications A and B have similar number of requests, application A spends surprisingly larger fraction of cycles stalling for memory than application B does. What's the reason? So assuming that we are using a first ready, first come, first serve, a possible answer to this question is that application A has such a large fraction of cycles because there are many row buffer conflicts for application A. Luckily, it's much better for application B, probably many row buffer hits. The second part B says application A also consumes a much larger amount of memory energy than application B does. What might be the reason for this? It's again because of row buffer conflicts, because row buffer conflicts consume more energy because they require pre-charge, activate, and read-write. So if the amount of energy consumed by another application, in this case application A, application A consumes more memory energy. So for example, application B that we are assuming that it has more row buffer hits. This means that we don't need to continuously close and open new rows. So because we are hitting the row, so that's why the consumed energy is less, is lower. Part C says when applications A and B are run together on the machine, application A's performance degrades significantly, while application B's performance don't degrade as much. Why might this happen? So it's important, this is interesting because we have to keep in mind that applications might interfere with each other. So in this case, if we have, as we are assuming, a memory scheduler that favors row buffer hits, like the FRFCFS scheduling policy, probably this memory scheduler is favoring one of the applications, in this case, application B, because it has many more row buffer hits than application A. So that's the reason why the performance of application A degrades much more. Part D tells us to consider a smarter policy to refresh main memory. And now the idea is that one row is going to be refreshed only if it has not accessed the past 60, it has not been accessed during the past 64 milliseconds. And it says, is that a good idea or not? Well, this can be a good idea because it's obviously going to reduce the amount of energy spent on refresh. Also, this is going to affect the amount of energy that is going to be spent by each application. So if we have a large fraction of rows that have been accessed, well, they won't be refreshed every 64 milliseconds, so we can have an improved refresh outcome. The last part E, says the refresh energy consumption when application B is run drops significantly when this new refresh policy is applied, while the refresh energy when application A is run reduces only slightly. Is it possible? Well, again, this is related to the memory footprint of the application. So, for example, in this case, we can consider that application B has a large working set, while application A has a much smaller working set. So, because this working set is much smaller, the number of rows that is going to be accessed is much smaller, so they won't be refreshed every time they are accessed, they are open or closed. So they will still need to be refreshed every 64 milliseconds.
Okay, we are solving now the question 5, that is about banking on caches on memory. Well, I'm going to read the question first. So a processor's memory hierarchy consists of a small SRAM, L1 cache, and a large DRAM main memory, both of which are banked. So the processor has 24-bit physical address space and does not support virtual memory, meaning that all the addresses are physical addresses. An application has just started running on this processor. So the following figure shows the timeline of memory references made by that application and how they are served in the L1 cache or main memory. So we can hear this is the part of the cache access timeline, and this is the memory access timeline. So this is the time. For example, here, when accessing this address, we have a miss, and when we access the next address, we have here a bank conflict. The bank conflicts are represented with this in these areas here, these green areas in this case. So here we have bank conflicts. So, okay, I will continue reading. For example, the first memory reference made by the application, so this one, is to byte address, this address. We assume that all references are byte-sized reads to byte addresses. So, however, the memory reference misses in the L1 cache. So here, assume that the L1 cache is initially empty. So immediately afterwards, the application accesses main memory. So in this case, we miss here and we access main memory. Where it experiences a raw buffer miss, this case here. Initially assume that all banks in main memory each have a row open that will never be accessed by the application. So eventually the cache block, and only that cache block that contains the byte address, this one, is fetched from memory into the cache. So at the end of this access. Subsequent memory references may experience bank conflicts in the L1 cache and or in main memory, if there is a previous reference still being served at a particular bank. Bank conflicts are denoted as hatch shapes in the timeline. So in the case of memory, the bank conflicts are these ones, all these, all these, all these, and all these. So in the table, we have the hexadecimal and binary memory addresses. Okay, so we have some assumptions. So from the above timelines and the table, your job is to answer questions about the processor cache and main memory organization. These are the assumptions. In L1 cache, the assumption for the block size is that power of 2 greater than 2, so meaning a minimum of 4. For the associativity, the same, minimum of associativity 4. Total data store size, the same thing. Number of banks, the same, minimum of 4, greater than 2, power of 2. And for the main memory, you assume one channel, 1 RAM per channel. Banks, the number of banks is a power 2 and greater than 2, so the minimum of banks is 4. Number of rows per bank is 2 greater than 2, so minimum of 4, minimum. Number of cache blocks per row, power of 2 greater than 2, the same thing, 4. The memory contains the entire working set of the applications and initially all banks have their 0 row open, which is never accessed by the application. So first, in the 5.1, some basic questions. So the A is cache and main memory are subdivided into multiple banks in order to allow parallel accesses. What is an alternative way of allowing parallel accesses? So the answer, as Onur explained in his lectures, is multiporting or duplicating. The question B is a cache that allows multiple cache misses to be outstanding to main memory at the same time is called what? The answer is non-blocking or lookup free. Question number C is, while cache misses are outstanding to main memory, what is the structure that keeps bookkeeping information about the outstanding cache misses? This structure often augments the cache, and the answer is miss status handling registers. The next question is, which is larger, an SRAM cell or a DRAM cell? The answer is the SRAM cell, because it has more transistors, occupies more area. So related with this question, the next one is, what is the number of transistors and capacitors needed to implement each cell, including access transistors? So for a regular SRAM cell is 6 transistors, and for DRAM is 1 transistor and 1 capacitor. So let's switch to the interesting part of the question, that is about cache and memory organization. So for the following questions, assume that all subsets and indexes come from contiguous address bits. So what is the L1 cache block size in bytes? So for calculating the block size, it's enough to know where the offset, how much offset bits we have in for indexing the bytes inside the blocks. So we can divide the addresses in 2 parts. One is the offset, and this is the part where we identify the block itself, and this is within a block. So we can focus on this heat that we have here in the cache. We're talking about the cache, okay? So for heating in a cache block, we have to access to the same cache block, meaning that this part of the address have to be the same, and this offset could be the same or different. So, for example, if looking at this address that corresponds in binary to this, to having a hit, we need to match these bits. That this could be, for example, the bank bits plus the tag plus the index, for example. This could be in other order, but let's consider all these bits that are the bits that identify a block in the cache. So these bits have to be the same. So, for example, we can assume, for example, that these are the bits that identify the block, and all other bits are the offset. We can see clearly that this is not the case, because if this is the case, for example, in the next axis here, we will have a cache hit, because we have the same bits here. These and these are the same. So this cannot be the same. So we can take more bits and see that this is the same case with the next address. So this cannot happen, because in the next address we have a miss. And if we assume these bits here, we will have a hit. So this is not possible. If we get more bits, we have the same situation. We don't have a hit here. So this is not possible. If we get all these bits to identify the block, and only these bits for the offset, we see that this is coherent with the next axis because it's a miss. These bits are different from these ones. And if we look in all other axes, we have the same bits here. So this could be a hit in this block. In this case, we have different offset. We are accessing to different words inside the block. Yeah. So if we assume one more bit, we wouldn't have a hit here because this bit is 0 and this is 1. So the correct answer is having an offset of 4 bits. And this means that you have a block size of 16 bytes. Yeah, this is the answer for the first question. So the bit position of the block offset is from 0 to 3. So, questions here? So for the next question is how many banks are there in L1 cache? Which bit positions in the 24-bit physical address corresponds to the L1 cache bank index? So having the same figure here, so now we will focus on the bank conflicts, so in these areas here. In these bank conflicts. Okay, let's see the memory address table. So we conclude from the previous question that these bits are for the offset. So we don't care about this. So our goal is find the bits that are mapped to the bank, to the banks. So we can start from the beginning. So we have here a bank conflict. If you have a bank conflict, it means that the bits corresponding to the banks are the same. So possible candidates for the bits corresponding to the banks are the bits that are the same. In this case, we have these, and also you have these two. Okay, these are possible candidates until now. If we see on the next axis here, we don't have bank conflict, so this is not conflicting with the previous one. So if it's not conflicting, means that the bank bits are different. So the bank identifier is different. So if we take these bits, we see that are the same. So this cannot be the bits corresponding to the bank. So we can eliminate these candidates. And we see here that you have a different value. So this will be the bank 1, and this is the bank 0. So this is coherent what we are seeing here. We don't have conflict because the bank are different, and this bank are the same. In the first two, the bank are the same, and in the next, the bank is different. So we just can conclude that these two bits are for the bank. You can conclude this because we previously see that the minimum number of banks is is 4. So with 2 bits, we have 4 banks. So we cannot have less than 4 banks. So these are the bits that are indexing the banks. So we have 4 banks. And the bits, bit positions are 4 and 5. Questions? So next question is about also about the banks. How many banks are there in main memory this time? So which bit positions in the 24-bit physical addresses corresponds to the main memory bank index? So we can do the same thing here. So now we are focusing on the memory, and we can observe, we can make some observations from this figure. First, we have row buffer miss. In the next axis, we have a conflict, which means that they are accessing the same bank. The next axis, we have also a conflict, which means that it's accessing the same bank. And in the next, at this time, we have also one conflict, which means that we are accessing to the same bank. So this means that the 4 first addresses are accessing the same bank. So this means, so let's go to the address table. We can discard these bits here because are the offset inside the cache line, the block. So these are not candidates. Then we have between the first 4 addresses, you have the bank bits should be the same. So possible candidates are these bits are the same, and also these bits are the same in these 4 cases. So possible candidates for banks are so far these. So the next axis is this one. We don't have a bank conflict. So this means that this axis doesn't conflict with the previous axis and with the axis before, and even with the axis before of this. So this means that the bank address should be different. So we see here that these bits are equal to the previous bits. So we can discard these bits because they are equal, but the bank is different. We don't have a bank conflict. So we only have these candidates, these 3 bits as candidates. So the possible options that we have until now is that these 3 bits here are indexing the bank. But with this information, the bank could be also indexed by only these 2 bits. Only these 2 bits. Because these 2 bits, so this is, in this case, is 2 and this is 3, so it's different. So could be only these 2 bits. These other 2 bits couldn't be because the value is the same than the previous one. So we discard this couple of bits. In the next axis, we don't have a bank conflict with the previous axis or the axis before. You have any bank conflict here. So it means you have these 3 candidates. We can see that if we choose only these 2 bits, we will have a conflict with the previous accesses, a bank conflict with the previous access. So we have to discard also this option of being 2 bits. So the only option that we have now is that these 3 bits are the bank indexes. So this, so we have 3 bits for indexing the bank. So the number of banks will be 8 banks. And the bits are from 10 to 12, I think. Yeah. Questions? So the next question is, what kind of interleaving is used to map physical addresses to main memory? So what we have until now is this. You have 4 bits for the offset. We have 1, 2, 3, 4, 5, 6 bits here that we don't know yet what are these bits for. Then we have 3 bits here for the bank. Then we have the rest of the bits here that are 11 bits here. That we don't know what they are for. So to identify, so we have 2 options. This section identify the column inside the row or the row itself. So I'm going to use this clean sheet. Right. 4 reads, 6 reads, 3 reads, 11 bits. Bank offset. So now we are going to look at the row buffer hit rate. So, for example, so again, these are the bits for the offset. We know this, and we know also the bank Bs are these ones. Okay. So we can forget about this. And so if we look at the raw buffer hit, so if we have a raw buffer hit, it means that we have the same, we are accessing to the same raw buffer. So the raw buffer should be the same. So if we look, for example, here in the first case, have these bits, and we can see here that these bits are equal and here are different. So it means that because we are having a row hit here, it means that these bits here are for identifying the row, and these bits here are for indexing the column inside the row. So coming back to the question, what kind of interleaving is used to map addresses to the main memory? So having this into mind, we see that these are raw interleaving. We are using a raw interleaving mapping because here you are indexing the consecutive. So this is the raw identifier per bank. So this means that consecutive rows are in consecutive banks. So it's a row interleaving. And this index, the column, the cache lines inside one row. But this identifies the row. That in this case, consecutive rows are going to different banks. So, questions? So, the next question, to fully support 24-bit physical address space, how many rows must each main memory bank have? Which bit positions in the 24-bit physical address corresponds to the main memory row index? So we already answered this, I think. So the question is, how many rows must each memory bank have to fully support the 24-bit physical address space? So as we saw this, we have 11 bits per bank to identify the row. So the answer is 2,048 rows. And the bit positions are, these ones are from 13 to 23. And the last question for this question 5 is, each cache block within a row is called a column. Well, we already know that. How many columns are there in a single row? Which bit position in the 24-bit physical address corresponds to the main memory column index? So it's the same thing. We have the columns here. We have 6 bits per column, so the answer is 64 columns. And the bit positions are from 4 to 9, these bits here.
Okay. Let's quickly go through question 6. In this question, we have a magic RAM, which is a non-volatile memory, and it is 2 times slower than an SRAM. And the access latency is similar to DRAM's cell. The dynamic energy of magic RAM is similar to DRAM, and actually the cost of magic RAM is similar to DRAM too. And magic RAM has higher density than DRAM, but magic RAM has an endurance problem. It means that after 2,000 writes to a cell, the magic RAM is weared out. So in the first question, it asks the advantage of magic RAM over the DRAM. So obviously magic RAM does not need refreshes, which means it reduces the power consumption, and also now we have better bus utilization and less bank contention. And also magic RAM provides the non-volatility, which means it brings new opportunities for the programming models. And question B, it asks about the advantage of magic RAM over the SRAM. So magic RAM has higher density and lower cost compared to SRAM. In part C, it asks that does it make sense to add magic RAM anywhere in this memory hierarchy? So the answer is yes. We can use magic RAM as a part of the address space in option 2. When we have when we have L2 cache miss, we can have DRAM access or magic RAM access. So magic RAM actually keeps part of the address space. Or it can be the whole address space in option 1, and DRAM actually is acts as a cache for magic RAM. So this is the 2 possible options for adding magic RAM. For example, we cannot insert magic RAM between L1 and L2 because the access latency of MagicRAM is slower compared to SRAM, and it doesn't make any sense to add MagicRAM there. So, and what can we do for reducing the overheads or mitigating that endurance problem? So actually, if we use DRAM as a cache for MagicRAM, actually DRAM is filtered some write accesses to MagicRAM, and it's good. But what we can do more is adding a write buffer between DRAM and MagicRAM. It can be used for coalescing or combining writes. And also, we can use some real leveling techniques to try to uniformly distribute the writes to MagicRAM cells. It can, we can have good endurance if we uniformly distribute the writes. So we don't write to one cell 2,000 times and to other cells only maybe 1 time. And also, if we use MagicRAM as a separate address space, we can have a technique to dynamically detect some pages that are mostly read-only, and then we can allocate those pages to MagicRAM, and it's good to have a good endurance for MagicRAM. Yes, that's all. Okay, let's go through question 8. In this question, we have a very good prefetcher. In parts, it's a prefetch block A before it is required with the load instruction. It means that it has a good timeliness. And also, prefetch blocked some blocks should be evicted from the cache to insert block A. But the good thing is that we evict a block that is never to be used, which means that a dead block in the cache. So, and actually, our prefetcher doesn't waste the bus bandwidth for another request. So actually, it's a good prefetcher. For the part B, we have the same situation for prefetching block B. So after executing the program, we see that prefetching block A has a significant influence on the performance, but prefetching block B doesn't have a good performance improvement. So what would be the reason, actually? So we definitely find out that block A is the miss for block A is a very important miss. So actually, if we prefetch block A ahead of time, we will have a significant performance improvement. But mitigating miss for block B is not important. So one possible reason could be the memory parallelism. Maybe we have 2 parallel misses to block B, or other block is maybe it could be block C. So if we bring block B to the cache and we don't resolve miss for block C, so we will not see much improvement due to mitigating miss block B. So it could be one reason for this. And actually, it can have other reasons. For example, maybe when we have fine-grained multi-threading, maybe we can, for some reason, we can hide the latency of the miss B. So in the baseline, when we have miss B, the processor is not stalled because we have other active threads that could be scheduled for the execution. But for miss A, the processor would be stalled. So if we resolve the miss A, we will have performance improvement. But if we resolve miss B, we will not have performance improvement. These are 2 possible answers to this question.
So this question is one of the questions that appeared in the final exam last year, which is about the DRAM refresh. And for this question, actually, we are given multiple refresh policies, and based on these refresh policies, we are asked to solve the questions basically. So to do this, actually, we have a memory system where we have 8 banks, and each bank contains 32K rows. So let's just immediately calculate the total rows, which is 2 to the 18. So, and we also have a table where it shows like some certain rows, which shows the retention times of the certain rows given the temperature. So let's jump to the first question then. So we are given a refresh policy, which is called a refresh policy A, and in that question we have a refresh interval which refreshes all the rows in a DRAM, which covers the worst case retention time. What does it mean? So it means that given a temperature, it refreshes all the rows where according to a row where it has a lowest retention time. So according to this table, we will have our smallest retention time here, because it will always give us the smallest retention time unless the temperature is 0. So given that the A says that, let's assume that the refresh interval is 32 milliseconds. So what can be the maximum temperature so that the DRAM can operate reliably? So basically I will take this one and solve the T given the refresh interval, which is 32 milliseconds. So the T will be basically 96 Celsius degree, and so that the DRAM can operate reliably given this refresh policy. So this was the first question, and it also asks what the command bus utilization is directly caused by DRAM refreshes. So command bus is defined as follows. So memory controller sends the refresh command, and the bus kept busy for certain time interval, which is 5 nanoseconds. So the command bus the utilization is basically what is the total time that the command bus is kept busy within a refresh time interval. So we can calculate it as follows. We know that all the rows will be refreshed, which is 2 to the 18, which will take 5 nanoseconds which will keep the bus busy 5 nanoseconds for each row. And for all of the rows, this will be the time that the command bus kept busy. And the refresh interval is 32 milliseconds. Okay, so this is basically the fraction of the command bus utilization, and this number will be, I believe, 0. Let me check. Yeah. So the percentage is basically this one. All right. So this was the first question, first policy, let's say. So for the second policy, it says that the memory controller refreshes the rows when it is needed. Basically, what does it mean? So given a temperature, if you need to refresh a row, based on this table, the memory controller basically refreshes it. So we are given a temperature which is 64, and let's just directly calculate the retention time, basically for this one, because the rest of them will be just the multiplication of the first row. So it will basically be 128 minus 64, and the retention time will be 64 milliseconds. So the question asks how many refreshes are performed by the memory controller during 1024 milliseconds period. So basically we need to find the number of refreshes for each of them. So let's find out. So the retention time for, let's make sure that this table is also visible. Anyway, so the retention time for the 2 to the 8 number of rows, here it comes from there, is 64 milliseconds, and then within that time period it will be that many times, right? So basically this will be the number of refreshes for that many rows. And for these rows, we will have that number of refreshes, because this is basically 2 times 64. And for this one, all other rows, we simply calculate it as the total number of rows are 2 to the 18 minus 2 to the 16 plus 2, basically the number of rows that are visible here. So for that many rows, we will have that many refreshes, that number of refreshes, and for the last one, we will have that many refreshes. So if you basically sum these refreshes, you will get this number. So I won't do the math here, but this will be the result of this one. So this was the second policy. Let's jump to the third one. So basically this is the same policy with the first one, where we take the worst case in the retention time, and then memory controller refreshes all the rows based on this retention time. And the retention time is actually given also here. So the memory controller will refresh all the rows for each 64 milliseconds. But there is also one more condition here. The memory controller will only refresh the row if it has not been accessed within that time interval. So if the row is accessed within 64 milliseconds, the memory controller will not refresh it. So basically, the first question asks this one: why is the case? Why can a memory controller should can behave like this? Do you have any guesses for this one? So why can it behave like this? Why can skip the row? Yeah.
Because the set is recharged on every access.
Yeah. Was it the same for you? Yeah, that's basically the case. So when you access it, the cell will be recharged after it is sent to SAMS amplifier. So yeah, this is the case. So let me formalize it. The charge of DRAM is restored basically when it is accessed. So this is the reason. So for the second one, we are given a program where the program actually accesses the rows with that fashion. Basically, for that many number of rows, it accesses each 1 milliseconds, and for that many number of rows, it accesses for each 60 milliseconds, and for the rest of them, it accesses for each 128 milliseconds. So, and the retention times are given for the rows that are being accessed in a given in a given row. And the question asks here, what command pass utilization is directly caused by DRAM refreshes. So remember that the retention time was 64, so the refresh interval will also be 64 for all of the rows. But the program accesses these rows before refresh takes place in 64 milliseconds. So this means that that number of rows will already be accessed, so we won't need them to be refreshed again, ever. Because this guarantees that these rows will be accessed before a refresh takes place. So we basically say that for these there is no refresh takes place by memory controller. But for this one, we can calculate it. So let's do it. So basically the number of rows left here is 2 to the 18 minus 2 to the 16 plus 2 to the 16. And this will be, I believe, 2 to the 17. Yes. So these are the number of rows that will be refreshed. And remember, the bus kept busy for 5 nanoseconds, so the utilization will be 2 to the 17 multiplied by 5 nanoseconds. So we need to divide it by the refresh rate. But remember, the refresh rate will not be 64 anymore, because we will be refreshing those rows once for each once in each two refresh intervals. Okay, so the refresh interval will basically be 128, not 64. Okay, and this will result, I believe, like this. And this can be written as like this as well. Yeah. So the last question, the question for the last policy is a bit tricky. So we have a balloon filter for this policy, and the memory controller checks the balloon filter if the row is located. If the retention time of that row is basically defined by the first row. Okay, so if the balloon filter says yes, the memory controller basically refreshes such rows for each 64 milliseconds. If not, it will refresh it for each 128 milliseconds. So this is basically the policy of this memory controller. So if you remember, the balloon filter can't say no if the data is already there. Like if within the bit vector, within the balloon filter, if the data is already located, and if you ask for it, it can't say no. It will for sure say yes. There's a data there. But the other feature of the balloon filters is that it can say yes, even though the information is not there. So there is this false positive behavior of these balloon filters. So basically what it means is that it can say yes. Like, for example, let's take a row which shouldn't be refreshed within 64 milliseconds. Let's say this should be refreshed in 128, and it says, like, is it located in the balloon filter? And if the balloon filter says yes, then this is false positive. Okay, this is basically what it is. So the question asks for the false positive rate. and we are given temperature here. So as I said, it refreshes the rows that are located in the Bloom filter for each 64 milliseconds and the others for 128 milliseconds. And it says that within that time interval, within 124 milliseconds, we have that many refreshes. So let's define P as the fraction of the rows that were false hit in the Bloom filter that should have been refreshed within 128 milliseconds. So this will be my fraction. Okay. So basically, let's write like this. So we have 2 to the 8 rows here that should actually be refreshed within 64 milliseconds. Plus, we have 2 to the 18 minus 2 to the 8. This is the rest of the rows that should be actually refreshed within 128 milliseconds, and this is the fraction of the rows that were false positive. Okay, so basically this is the number of rows refreshed in each, let's say, each 64 milliseconds, and this is our false rows. So, and how many times those are refreshed? So this is within that period. So this is basically number of refreshes for 64 milliseconds, let's say. Plus, we also have 2 to the 18 minus 2 to the 8 multiply minus 2 to the 18 minus 2 to the 8 multiply by I guess, yeah. So basically these are the rest of the rows that should be refreshed in 128 milliseconds minus that are actually refreshed here. Okay, and this is again the number of rows in 128 milliseconds. So if you sum this one, this number is actually given here. It's 2 million something. Okay, we already formalized it. So basically what you need to do is to find what P is. So if you do the math, the P will be this. Okay, this is the fraction of the rows that should have been refreshed within the 128 refresh rate. So what is the number then? What is the number of the rows? It is okay, and this will give us. So these are the number of the rows that were false positive, that were hit by the Bloom filter. And what are the total? And our fraction will be basically the total number of rows is this, and this is the false positive rate. And this is what the question asks for.
So this question is about prefetching. Hope that you guys are enjoying the prefetching lab. So yeah. So okay, let's read the question first. So an ET student writes 2 programs A and B and runs them on 3 different toy machines M1, M2 and M3 to determine the type of prefetching mechanism these machines are using. Now she observes that program A and B to have the following request access pattern. The access pattern is shown like this, And so these access patterns are actually to the cache block, but not the actual cache address, not the block cache block addresses. Yeah. So yeah, program A actually has 27 accesses, whereas program B has 501 accesses, and the access pattern goes like this. And then the student is also able to measure the accuracy and the coverage of the prefetching mechanism in each of the machines, and the coverage and the accuracy for each of the machines for each of this program looks like this. So now there are some more information that we have is this. So basically so the first information says that the prefetcher prefetches into a fully associative cache, which is an 8 cache block wide, and the prefetchers have large enough resources to detect and store all access patterns. Third one is each cache block access is separated long enough in time so that the prefetch issue can complete before the next access happens. So that means there is no problem of the timeliness. And there are 5 different possible choices for the prefetching mechanisms that we know beforehand. So the first 2 are the Markov prefetcher, 3 and 4 is a variant of a next block prefetcher, and the 5th one is a stride prefetcher. The first 2 basically says that Markov prefetcher which can learn and store up to 4 entries, second one can store up to 10 entries, third one is just the next line prefetcher, like the next block, exact next block, and the 4th one is the 4th next block basically, and the 5th one is the stride prefetcher. So now the question is that none of them have any confidence bit, and they starts with empty table and everything is fine, and then the prefetch degree is only 1. So that means we only send 1 prefetch request for each demand access. So now the question is that so determine what type of prefetching mechanism each of the above mentioned machines use. So the first approach to solve this problem is, whenever you see this kind of question in exam, it's better to simply just go with this program access pattern and just evaluate how this program would behave, like how a normal let's say these prefetchers, these 5 type of prefetchers would behave for this access pattern. So I'm jumping straight towards the solution itself. So I have the solution printed out because it's like too much writing, but let's go through the solution. So if you recall, what is a Markov prefetcher? Markov prefetcher basically understands the correlation of the cache block addresses. So basically whenever you have a cache block address A and A plus 1, so it learns that A plus 1 is followed by A. That's the correlation it's learning. Similarly, it actually learns A plus 2 is followed by A plus 1, A plus 3 is followed by A plus 2, and so on. So the idea of prefetching in this context is, whenever you see, let's say A, it would actually issue a prefetch for A plus 1 after that. So that's the Markov prefetcher, right? And we know that table size basically determines that how much information you can store, how much knowledge you can store actually. So let's see. So in the first case, we have this 27 accesses from program A. So now let's see, if our Markov table prefetcher has only 4 entries, so that means it can learn, so let's say A plus 1 is followed by A, that's 1 entry, A plus 2 is followed by A plus 1, that's another entry, and so on. So that means by the time it actually reaches A plus 4, so you have 3 learnings, A to A plus 1, A plus 1 to A plus 2, A plus 2 to A plus 3, and A plus 3 to A plus 4. That's 4 learning, right? Now if you go to A plus 8, you are actually dropping the first learning, and A plus 8 is something which is completely new to the prefetcher. Prefetcher actually haven't seen this cache block address before, so it cannot make any prediction in this case, right? So if we just extrapolate the entire thing, so it's just learning something, it doesn't have enough storage to apply its learning, so that means it's not prefetching anything at all, because none of the addresses are repeating, and when the address actually repeats, by that time it actually forgot everything because it doesn't have enough information to store. So that's why its coverage is 0, accuracy is 0. It's not prefetching anything, coverage is also 0. But accuracy should be 100% technically, but yeah. But okay, so let's go to the second case. So the second case is basically like you can actually store A plus 1 followed by A, and so on, right? So if you see how many entries are here, that's 9 entries. So that means a 10 entry table is actually can store up to this entry, that A is actually followed by A plus 64. Till this you have the knowledge. Now the prefetcher actually sees that okay, A plus 1 came again. Now A actually came again, so it start prefetching A plus 1 because it has enough storage to remember that A plus 1 is always followed by A. So that means any further access is actually prefetchable. So in this case then we can see that okay, the coverage is 17 out of 27 accesses and the accuracy is 17 out of 18, which is like pretty accurate. Make sense? Okay, now let's go to the second one, third one. So third one basically says the next block access. That's a very basic prefetcher. So A predicts A plus 1, A plus 1 is good. A plus 1 also predicts A plus 2, A plus 2 is also covered. A plus 2 predicts A plus 3, A plus 3 predicts A plus 4, everything is covered. So that means A plus 1, A plus 2 and A plus 3 and A plus 4 is predictable. Right? Now A plus 4 will predict A plus 5, which is not present. So that's completely gone. Now A plus 8 will predict A plus 9, which is also gone. I mean, program is not accessing this one. So none of these accesses are predictable. So that means out of these 27 accesses, only this 12, right? Yeah, only these 12 is on predictable, nothing else. Does it make sense? Stop me if you are not following me at any point. Okay. So in this case, then what is the coverage? Coverage is 4 out of 9, and the accuracy is 4 out of 9 again. Okay. Yeah. Ideally, we should measure accuracy based on how much you prefetched. Well, okay, so yeah, so in this case, the coverage is 4 by 9. Is it clear? Right? Okay. So let's go to the fourth type of prefetcher. So that's the fourth next block. Okay. So fourth next block, again the same thing. A plus 1 is not covered. A plus 2 is also not covered. A plus 3 is also not covered because nobody can actually prefetch this for these guys. A plus 4 can be prefetched from A, because that's a fourth next cache line. So that guy is covered. A plus 8 is also prefetched by A plus 4. That means this guy is also covered. Anything apart from these, it's not covered. So then these are also gone. So again, you can come up with the coverage numbers and the accuracy number. Make sense? Now let's go to like a more complex prefetcher. Let's say stride prefetcher. So stride prefetcher does what? It just learns the last stride it actually seen, and it just applies that stride again, right? So whenever it actually sees A plus 1, the last access was A, it learns that there is a stride of plus 1, it just prefetches for the next stride. Then A plus 2 is covered, right? Similarly, A plus 1 and A plus 2, it learns plus 1 stride. A plus 3 is also covered. Similarly, A plus 4 is also covered, right? Now let's think, A plus 4 and A plus 3, it actually learned a stride of plus 1. So it will probably prefetch for plus 1, A plus 5. The program generated A plus 8, so you are not covered. A plus 8 and A plus 4, it learned a stride of 4. It will prefetch A plus 12. But actually program made a demand request to A plus 16, which is also not covered, and subsequently none of these are covered. Is it good? So that means we again ended up having these many of the covered requests and none of them are covered from this access pattern. Make sense? Okay, so now let's move to the second program. Okay, so the second program, as we have seen, the second program is this, right? So it's just 501 accesses, and it's a arithmetic arithmetic progression. So B plus 2, B plus 4, B plus 6, and so on, B plus 998, B plus 1000. So you can easily guess the stride prefetcher is going to work very well in this case. Okay, so now let's see Markov prefetchers. Now think of this, none of the cache line addresses are repeating, so Markov prefetcher is useless in this case. It doesn't matter how many entries you can store, both of them is useless. So Markov prefetcher, second program, useless. 0 0 0 0. Okay, now let's go to the next block. The first next block, well, we are not doing the first next blocks anyway. Again 0. Fourth next block, some of them can be covered. So let's see. So B plus 2 doesn't have any candidate to issue prefetch for this guy. So B plus 2 is uncovered. B we cannot cover anyway. B plus 4, yes, we can cover. B plus 6, B plus 2 will generate for B plus 6. So B plus 6 is covered, and subsequently everything is covered. So that means apart from the first two axes, everything is covered. Make sense? So that means its coverage is pretty high and everything is good. Let's look at the stride prefetcher. Stride prefetcher is again the same thing. B and B plus 2, it actually learned a stride of plus 2 and it applied the stride again. And as the program actually behaves very regularly, that it just repeats the stride 2 again and again. So it just simply covers everything, right? So that means we actually ended up having two prefetchers for program 2 which exactly has a similar coverage and accuracy. I mean, accuracy is a little bit off, but almost similar. So now once you have done this entire calculation, let's say exhaustive calculation for all of these workloads and the prefetchers, you just tally up with these guys which one of them actually matches, right? So program B and for machine 1 and machine 3 is almost the same thing. So that means you know that okay, either it can be the next plus 4 or let's say the stride prefetcher. But as we have seen that okay, program A has different property, we can simply go and check which one fits best, and that essentially ends up here. So machine 2, everything is 0, that means it's most likely Markov prefetcher. So yeah, Markov prefetcher, it's out. And then machine 1, it's fourth next block, and machine 3 is the stride prefetcher. Make sense? Good. Yeah.
For the fourth next block prefetcher, program A on the bottom, on the other side.
Yeah, sure.
Is the reason that we can do like A plus 8, or sorry, A plus 4 from A? Do we know that because of the property, like in the beginning where it says the prefetchers have 8 cache blocks to insert stuff, so that it hangs around, right? When you prefetch from A to A plus 4, it hangs around despite you prefetching for A plus 1, A plus 2, A plus 3, it still stays there because our cache is big enough.
Oh, no. So the program actually demands these guys, right? So now think of this. So whenever the program demanded A, the prefetcher knows that whatever is demanded, I'm just fetching 4 cache blocks ahead. I'm just fetching the 4th cache block ahead, not 4 cache blocks. So whenever program accesses A, it will actually inject a prefetch for A plus 4.
Okay.
Make sense? Yeah. So A plus 1 and A plus 2, it just comes and uncovered. Now whenever the program actually touches A plus 4, it again generates a prefetch for A plus 8. So that's why A plus 8 is also covered, and nothing else is covered.
Okay.
Does that answer your question?
I think so, yeah.
Okay. Yeah, good.
But how long does A plus 4 actually stay for in the
in the cache?
Oh yeah, does it depend on...
Well, okay, yeah. In the ideal scenario, yes, it actually depends on the cache. But as we have said here that wait. Yeah, I mean the prefetches into a fully associative cache whose size is 8 cache block. I mean it's big enough to hold. 8 cache block means you can simply think of 8 cache blocks, like prefetch cache blocks you can hold, right? So by the time the demand actually comes, it should not, like the demand and this prefetch should not be 8 cache blocks ahead, which is not happening. So yeah. Okay.
This cache has both the actual accesses and the prefetched accesses.
This one?
This cache, these 8 cache blocks will have, so if we have A, it's A and A plus 4. And A plus 2.
I won't say that. Yeah, because it just says that it prefetches into a fully associative cache. Maybe you can think of it as a different cache, like a stream buffer or something. Yeah, but the idea is like if you have made a prefetch, let's say, I mean, you have made a prefetch to cache block X, and you have generated, let's say, 8 prefetches after that, and then this X is getting demanded, then X is gone. Does it make sense? Yeah. So yeah, I mean you can think of this as a prefetch buffer, but yeah, probably if you just add it to a normal cache, this will get complex. But yeah, let's not think about that. Is it clear?